Okay, so I think we can start. Welcome everybody to this to this last day of the first convenio of Società Italiana di Fisica e Statistica. This afternoon we have the pleasure to start with Jorge Kurchan from NS in Paris, which will talk us about an unexpected bridge between glasses and black holes, that I'm really eager to say. So please, let's leave the stage to Jorge without any further ado.
Okay, am I sharing correctly?
Not perfectly.
Wait.
If you can make full screen, will be better.
Yes, I am indeed trying to do this, which for the moment I don't. Yes, but where is it? Zoom, probably.
In Zoom, is there in Zoom full screen? No, in Zoom.
Yes, a full screen mode.
Full screen mode. No, down.
Yes. Okay, now I hope you're okay, no?
Now it's perfect. Please.
Okay.
Ottimo.
I have to stick. So, okay, so let me tell you about this bridge between these two subjects. So I am following these papers you see below, and this you probably don't need, but for those of you who might need it, a review where you can see the part of glasses I am using, you will find in this very readable review of Castellani and Cavagna. So I'm going to do the glasses quick and the more field theory thing slow, because I suppose that most of you know this story, the glass story. So glasses could be what? The most typical example would be an amorphous system of hard particles. This is a photo of Daniel Bohn of a colloid. Or it could be, as you all know, a spin glass where the interactions are ferromagnetic and antiferromagnetic, and thus the system has trouble in finding the best possibility. So the high dimensional problem, the spheres in high dimensions, is the most simple to grasp. It's very clear. And in infinite dimensions, in very high dimensions, this now is completely solved dynamically and equilibrium. And we find a lot of features. But the interesting point is that we find mostly the same kind of features in a model that is much simpler to write, which is you have like a spin glass with many many body interactions. The etas are now like continuous spins. They are commuting numbers, and they have to live on a sphere or on something that limits them, because otherwise the model is unbounded. It turns out that Kirkpatrick, Tirumalai, and Volines many years ago guessed that the phenomenology of this would be like the phenomenology of this, and their guess now is well established. So we're going to concentrate on this, also known as the p-spin. So three strategies, you probably all know about this. One is to calculate equilibrium. So if this is the landscape, and you're not supposed to ask me what is the x-axis, if this is the landscape, the deep states, the deepest of the deepest, to which you will never get, are the ones that dominate equilibrium. And this is what you get with the Parisi ansatz. This is the most traditional, if you want, point of view. Another one is to actually study the things like happen in experiments. You start in a configuration and let the system go and let in contact with the heat path. And then the system will spend its time traveling far away from the ground state, but forever approaching. And then a much less explored way is, well, a way that has been explored a lot is to count the number of valleys. What is less common is that it turns out that you are able to compute the number of states just by doing dynamics, but demanding that the trajectories be periodic. So if you count with their probability the number of trajectories that close after a year, you are calculating the number of metastable states whose life is a year, and then they decay. This is a result that takes half an hour in front of a blackboard to prove, but okay, it's not immediate, but it's not hard to prove. Okay, so as you all probably know in Italy, this is the solution that Giorgio Parisi found for the equilibrium situation. This is his ansatz. You start with a matrix that is like any matrix, has an integer dimension. You make blocks that are made of sizes inevitably that divide this size, and you attribute values according to the colors that I've drawn here, and then you dream an analytic continuation to n equals 0. I say dream because actually you don't know what a matrix of non-integer size is, but in any case, the recipe that Giorgio came up with, and now we know it's correct, gives the correct result, is to reverse the sizes of the blocks and keep instead the values you attributed. And then you ask that the saddle point equation be respected. In this case, the saddle point equation is written here. And please remember it. This is for the p-spin. Please remember it because it will reappear a little bit later. Please, if you want to stop me online. Don't wait till the end if you have any doubt. So the other strategy is to do dynamics, as I said, where you start with some situation and then you let the system go. The dynamical equations are these, and the order parameters are the correlation, eta eta, the response, which is also the correlation between fields and the noise, and the correlation of the noise and the noise, which is simply the correlations of the noise, and if we take it white, it will be a delta. At least in this setting, not in all settings, but in this one, it will be a delta. So just by doing what you probably most of you have done many times, you can get for exact equations, just as you can get for exact equations for the replica matrix, you can get two similar equations, but now for the correlation and the response. I don't want you to make an enormous effort to understand them. The only thing you have to realize is two things. First of all, they're very ugly. You won't expect them to solve them analytically exactly. And an interesting point is that this nasty object contains a derivative. This is the only time derivative. And this will be important in a second. So in the low temperature phase, the solution you get for this is that actually the system ages, which means that it goes on and on and on, but never quite reaches equilibrium. So what does that mean? It means that if I plot a correlation at a given time t star, if the t measured from the moment I made the quench, at short times the correlation drops, but as the system gets older, this correlation falls to 0 slower and slower. And now, if you want instead to calculate a response, you turn a magnetic field on and you see the magnetization going up. If you do so after a day, this part of the magnetization will grow in a day. If you do it after a year, the first part is the same, but then the second part takes a year to reach the other plateau. So this is aging. The system is getting more stiff as time passes. So here you have the famous experiments of Strauch, who did it with something very close to a plastic ruler. You compress the ruler or try to stretch it. You have a first part where it's completely universal, which is the immediate compression, the elastic. And then slowly the size creeps until it reaches a new size. This is just, think of it as a piece of these curves. And this has been done from 0.03 days, which is minutes, to 3 years. And you see that this goes on and on and on and on. As the system gets older, it is harder for it to perform this second step, but it does it, and it does it exactly scaling with the age. You see, the last curve, Strauch puts all the things together, and they sit perfectly one on top of the other. Okay, so one thing to realize is that when you look at these equations, this derivative, of course, we know now from the solution, you can put it in the computer, that this motion, the interesting part of the motion, the slow one, becomes slower and slower as time passes. So this means that the derivatives here, the red ones, are going to become smaller and smaller compared to the rest. And so at very long times, you can think that you can throw these derivatives away and just attempt to solve the black ones on their own. This is a crucial thing, and this is the crucial thing of this talk. This step, once you threw these away, is correct and is not correct. It has an element of correctness that you will see, and it has a little problem. So suppose I throw these to get the slow parts. And then I should say these equations have a unique solution. You can prove this just by writing the program that solves them. There is no moment where the program has any ambiguity. So this for me is a theorem. So they have a unique solution. However, when you throw the time derivative, it is no longer true. And why is this? This was discovered, I believe, at least by Sompolinsky and Zipelius in '83, and maybe it was even before that, I don't know. The point is this, that once you throw the time derivatives, what you get, the black equations here, have this reparametrization invariance. So you take the time, stretch it in any funny way, nonlinear way, and the equations remain the same. But this is very strange because I told you a minute ago that the equations have a single solution. And indeed, what happens is that of all the H's you can put, there is only one that is really good. But the system almost has a soft mode, almost has an invariance with respect to these reparametrization. And these almost invariance is true literally when you throw away the red guys. So the red guys are there to choose, if you want, between reparametrization, which is the good one. And this is not pure maths. Take the plastic ruler I showed you before, the one of Strauch, and every week during the first year, on Fridays, you take your ruler and you bend it back and forth 8 times, and then you put it back on your drawer. And what you will discover is that the dynamics keeps young at an age of roughly a week. So the ruler doesn't show any big difference. A ruler that is a week old is a perfectly good ruler, and it doesn't look very different from one that is 3 years old. But when you look at this creeping motion, it has become young. And why is this? It is because in doing so, this already Strauch himself did it, in bending back and forth the ruler, you have changed the reparametrization. Because the reparametrizations are all almost solutions, then going from one to the other doesn't require a terribly big effort. And in fact, bending back and forth your ruler every Friday will do. So as statistical physicists, what do you do when you have a situation like this? When we threw the derivatives, we have an almost symmetry. And this is purely metaphorical. You have almost a zero mode. In this case, it's a zero mode with respect to all reparametrizations. What do you do when you have something like this? Well, you do what these gentlemen here did. You try to make a kind of sigma model of these degrees of freedom that are almost a symmetry. And what you would call low energy or the almost invariant space will parameterize this almost soft mode. And it's a mode that becomes the softer, the more old, the more aged is the system. So what these people did, not quite till the end, but at least tried, and the papers are very nice and very illuminating, is they wrote a kind of action for this flat part. As you will see, this has going to be a connection in field theory, and it is what a field theorist would call an infrared theory, meaning low energy part of your problem. So if there are questions up to here, I would like to take them because I think it's important for the next step. Okay. Is someone listening to me, by the way? Hello?
Oh,
Yes.
claro, claro.
Yes. Oh, okay. Okay.
Okay. Maybe
Yeah.
I have a question. So a very stupid question. So where is the temperature in these equations?
Not really fantastically anywhere. Let me put it somewhere. It should have been here, sort of I factored it out. Don't expect great changes, provided you are below the transition temperature.
Okay, thanks.
Okay, so you have this almost invariance. Okay, now quick other thing. It turns out that if you plot correlations against responses, if you are in equilibrium, you get a straight line, universal line for any system in equilibrium, and this is called, chi is the integral of the integrated response. You get this line, which is nothing but the fluctuation dissipation theorem. This is just telling you that you're in equilibrium. When you do this with something that is aging, you discover, to your great surprise, that you get two straight lines, as if you were living in two different temperatures, one for the fast scale and one for the slow scales. This is a surprise, and it came as a surprise, and it required a lot of elaborating to understand where it comes from, but let's believe the surprise. So the system on its own, because it is out of equilibrium, of course, in equilibrium, this is forbidden. You can only have one temperature, but because it is out of equilibrium, it has developed a second temperature. And it is possible also to develop two more temperatures. So having in all three, if and only if you have three very separate timescales. The ruler that I gave you the example of is not an example of this. It only has two, but you can easily construct a system that has two and three and so on. So all in all, what you get, and to your big surprise, is that when a system is aging, it has two or more timescales. It develops on its own a different temperature for each timescale. And the temperatures, and this is important, have to be the same for the system, for the things to be consistent for all observables at the same time scale. So take any observable and look at it at a given time scale, take another observable and look at it at the same time scale, then their temperatures should be the same. Otherwise, the whole solution that I'm describing breaks down. Okay. But now what we now know, and this is in the papers I mentioned, is that in fact, at least in infinite dimensions, the solution of Parisi and the solution with timescales and temperatures imply one another. This is something we know now. So Parisi implies that you are going to have as many timescales as replica symmetry breaking steps, and that at each of these timescales, you're going to get a temperature, which is given, for those of you who are practitioners of Parisi's ansatz, by the temperatures divided by the axis of precisely Parisi. So when I say that the whole thing breaks down if, for example, all observables don't have the same temperature at the same time scale, this for finite dimension means that the Parisi scheme also breaks down and will not apply to such a system. So if you measure a system and you discover that it has a slow time scale, but in that slow time scale, the fluctuation dissipation relations lead to different temperatures in the same time scale, then you know that Parisi scheme is not applying. And here you have a big problem, because now you can say, but wait, how can both things ever work? Let me suppose I have a system that has a fast temperature T, which is the one of the bath, and a slow temperature T1. Let me take another system that has a fast temperature T, and it happens to have, and this is of course possible, another temperature, a different one for the slow variables, but a slow time scale. And these slow time scales happen to be at the same times. That's okay, because there are two systems. But now I couple them, and now I have a big problem. I have coupled two systems that follow very well the dynamical plus Parisi ansatz. And when I couple them together, it would seem that they contradict such coupling, because the combined new system, even if very weakly, will have two temperatures that are different at the same time scale. So we have a big problem of consistency of the whole story. And a miracle intervenes, and this is really the first time you hear it, it seems like an excuse, but it is true. When you couple two systems that would want to have different temperatures in the same slow timescales, the timescales kick themselves with the elbows, and the slowest one keeps one of the temperatures, and the other one becomes much slower, and it keeps the other temperature. For weak coupling, this is what we get. Even if the coupling between the systems was epsilonic. But now this seems like special pleading, and I promise you it is not special pleading. You can even justify it. This is what happens. But why can this happen at all? You are coupling very little two systems, and they are pushing, their time scales are pushing each other apart because they don't want to live together if they have different temperatures. Well, it may happen because precisely of the reparametrization quasi-invariance I mentioned before. It is possible for a system that has an almost invariance to do a lot with very little push. This is precisely what saves the day. So, message of my first part of the talk is the dynamical multi-thermalization, so one temperature per time scale shared by all observables, or the Parisi ansatz in finite dimensions, can only survive and be reasonably robust if there are, thanks to these reparametrization invariants, which now we understand are the actual, the real foundation of everything. Everything needs this, otherwise the whole thing would collapse. Okay, this is another point for you if you want to ask me a question. Okay, nobody wants to. So, okay, this you know less, probably most of you. So, you take this was a model which is a variant of another model. So it's Kitaev who wrote this model as a variant of a model that Sache de Venier had done many years ago. It's a quantum model. It has random couplings just like the ones I showed you before, only that antisymmetric, because these guys are either fermions or Majorana fermions. A Majorana fermion is just a symmetrized ordinary fermion. And you see that this is very similar, only that instead of being numbers that live on the sphere, as I did before, this is quantum and it's made of fermions.
Joseph, just
Yes.
one question. Are these interactions arranged on a plaquette?
No, no, this is everybody with everybody. It's the easiest of the easiest. It's mean field. All these IJKLs are all talking to all. Okay?
Very well, very well. Okay, thank you.
Now, okay, and what was known of these models is that it's a metal. Metal we call something that has no gap in this context. And it's a strange metal. And by strange, we mean that instead of having a few states that are quasi-particles, so what would be like waves, the lowest excitations are a mess. They are exponentially many. There is ground state, zero temperature entropy. And these excitations are nothing like a sequence of waves of higher or quasi-particles or anything like that. As such, Sachdev did a lot of it. But what happened in some 3 years ago, or 4 maybe, 5 maybe even, Kitaev, I don't know, don't ask me how, understood that this model, as you see it, you can take it as a model of a black hole sharing, or as a toy model of black holes and holography. You have to be him probably too. So, okay, let's see how you solve this. Well, not surprisingly, as you know, it's a quantum model. So we have to do the trace of e to the minus beta h. We have to do Matsubara. The time here is what a field theorist would call a Euclidean time. It's a time, the Matsubara time. But as you see, it's very, very near to what we were doing before. And you get to this equation. Now, if you remember what I told you before, if you really were following, remember that we had this equation for replicas, and you have this equation for a glass, so that this equation shouldn't surprise you too much. It's very much like those that I wrote, only that it's between 0 and beta, like in any case in which you want to compute a partition function in a quantum model. Very, very similar. And as you go to temperature, you discover that the correlation falls more and more slowly. It doesn't age. It's an equilibrium problem, but it still approaches a slow, slow, slow regime as you near 0 temperature. In other words, it becomes a true glass at 0 temperature precisely, if you want. And because of that reason, and for exactly the same reasons as before, the time derivative here becomes negligible. And because of exactly, so as I showed you before in the other equations, you would like to throw this. And once you throw this, you have in the window a reparametrization invariance just exactly as before. Indeed, it's not only analogous, it's basically the same story. And of course, your system, this is true only when it's very slow, because you only then can throw the time derivatives. And again, your system has this set of invariances, which involve taking times and stretching them as you please. And here, the project that these people here in orange wanted to do for spin glasses, which is to make a theory like a sigma model of the reparametrizations, Maldacena and Stanford did it exactly for this model. And the action of this model, the sigma model of reparametrizations, is this ugly thing here. Well, it's not ugly. For those of you who do conformal theory, you know this very well. This is the simplest thing you can do that has conformal invariance. This calculation was done by Maldacena and Stanford, but the guy who had the intuition of the whole thing, is no doubt Kitaev. So here the program is completed. Here I believe it is quite not complete, but it should be there and it is important. But let's say here it was completed. And this was a big surprise that once you do this, once you keep yourself at the level of the reparametrization invariance theory, you discover that this model here the SYK model has the biggest chaos you can have at very low temperatures. In other words, it saturates this thing, which is a bound. It's a bound that is unrelated to this. This is the largest Lyapunov you can have, quantum Lyapunov you can have. But, and here comes the surprise, this kind of saturation of the bound is exactly what you expect of black holes. And more or less, I should say, only of them. So, lo and behold, Kitaev realized that this spin glass was, in some sense, a metaphor, if you want, or some sort of super toy model of a black hole. And this is what created an explosion of interest. And then Maldacen and Stanford deduced this equation, rededuced Kitaev's things, but more, they showed that in a string at low, in ADS, anti-de Sitter, and at very low energies, this is something that also saturates the bound. So this thing here is both a simple string in low energy, so in the infrared, you would say, in anti-de Sitter and so on, which saturates the bound, but it is also the low level of SYK model. This is amazing. So, and it has a transition at zero temperature. The others, it has non-zero entropy as you go to zero temperature, just like black holes. So suddenly the beast, which is essentially a quantum spin glass and nothing else, and mean field on top of it, quantum spin glass, happens to have symptomatology of black holes, only that in this case, it is completely and absolutely and totally solvable. So you can imagine the enthusiasm for people who are accustomed not to be able to calculate much. Here they can really calculate everything and see what you learn. And so the analogy goes like this. The quantum field theory is the SYK model with its Majorana fermions. When you average, you get this thing which occupy a place like a string theory in general with everything. Because this is just a transformation of this. It is exact because we are in mean field, and this plays exactly the same role as the dynamical equations that I wrote for the glasses. And then extra step, which Chamon, Kenneth, Cugliandolo, etc. wanted to do for glasses has been done for here, which is you discover this symmetry that arises, almost symmetry, and then you write the effective, let's call it action, this parametrization symmetry. This gives you the lowest possible energies, the one that have to do with changing reparametrizations. And this is what in a field theorist would call infrared limit, in other words, gravity. So this would be a string, this would be the gravity of it. So you're going all the way from, because gravity is obviously the lowest energies of the theory of everything, no? So in other words, you have within this simple game, notice once again, this model is nothing much more complicated than what has been done by spin glass people all along. But it is a metaphor or a toy model of, or has the symptoms of holography. Holography meaning going from here to here. And the gravity theory here is the theory, remember the ruler whereby bending it back and forth, you change the reparametrization. That's for the ruler living in this part, in the most cheap part of the energy. I think that I should finish here, or shall I continue a little bit more?
In principle, you have more other 5-6 minutes. I don't know if you want to.
Okay, I will rush
some details of closer look and then leave stage to the question.
Okay, so I will go very quickly to this, but if you want to stay with one message, stay with this one. And then I'm going to go a little bit further. I told you that counting metastable states, and this is completely general, is doing dynamics, but summing all orbits that you force them to be periodic at a given lifetime. And when you do the dynamics on that, and you count with their probabilities these orbits, the number you get is precisely the number of metastable states of that system. We're talking about classical system. It's exactly the number of metastable states that the system have of this lifetime. If you are more picky and you want metastable states that live more, then you close the orbit at longer times, and the number that there are, of course, will be small. So when you have a situation where you have a Langevin equation that leads you to a Fokker-Planck equation, this is like the glass we were connecting to a system, you have this Fokker-Planck equation. This is purely classical, and you can transform it in a way that you will find in Parisi's book very well explained. You can see that this Fokker-Planck operator essentially like a Schrödinger operator. And through this thing, what you get is that any system that satisfies a Fokker-Planck equation, or Langevin equation, there is a direct connection between the eigenstates of that operator and the eigenvalues and the metastable states of the original system. Why is this interesting? Because if I have a glass, I have lots of metastable states with very long lifetimes. And this immediately takes me to the fact that the Fokker-Planck equation of evolution here has as many low-lying eigenvalues with eigenstates that correspond to these things with a lifetime where the value of the eigenvalue is 1 over the lifetime. So if your original glass had an exponential number of metastable states, its, let's say, Fokker-Planck operator, considered as a Schrödinger-like operator, has also an exponential number of quasi-degenerate ground states. This process of going from diffusion to a state, to a fake Schrödinger equation, which is nothing but the diffusion equation with a change of basis, is called Roxar-Kivelson, and they applied it very successfully. So you construct a quantum level, or a fake, if you want, quantum level, just by taking a dynamical system, stochastic system, and looking at its generator of evolution. The point is that because of this connection that I'm mentioning, if the original model was a glass, the Roxar-Kivelsonized quantum model, meaning the evolution operator of this one, is going to have zero temperature, if you want, degeneracy. So in other words, if you look at the evolution operator of a glass, it is the quantum, you can think of it as a quantum Hamiltonian of a strange liquid or a strange metal, depending on whether you're using or not fermions. So the connection is really super general. That was not a question, I suppose. Okay, so that's all, really, that's all. So this is, thank you very much for your attention.
Thank you, Jorge, for the very pedagogical talk on all the aspects. If there are questions, I can start with one, actually, with one curiosity, while the other people think of some question. The Sachdiev-Kitaev model is nothing but a quantum glass.
Yes.
As you said many times, but it's done with fermionic variable.
Yes.
Do you know if there is any analog, something with bosonic degrees?
So anything with bosonic degrees of freedom, yes. And in fact, any glass, if you take traces instead of the evolution from its evolution operator, is. But there is one difference, and to this, I don't really know. When you look at the low, so let me put it this way, you get a theory that would be something like the infrared limit, no? Now, This is for technicians, so it's for you, basically.
Yeah.
And Malte, who seems to be there. The residual group of symmetries here is, and you will recognize surely here, is a SL2 residual conformal thing. In the case of glasses, you still have a theory for H, but its group is a stupid group that is not SL2. It contains times translations and some internal supersymmetry, internal meaning between the fields, but it is not SL2. How important that is, I don't know. I mean, for here, it is, there is always a residual group and there is always a low energy, let's say an infrared, but that the infrared keeps a residual symmetry SL2. I've never met a bosonic system that does it. But if you're content with a simpler group of residual symmetries, I can make you a dozen.
Okay, so it's clear, but you don't get a black hole, then you get something else. And
I don't know, because I talk to people and they say, but I can also have my own black holes that are not SL2. So I don't know. Honestly, no, don't look at me. I have no idea.
No.
Not my cup of tea.
Okay,
but you get, yes.
Anyone else has some question?
Maybe I just want Matteo Marsili. So can you explain a little bit better this Lyapunov exponent and this
yes,
saturation of this?
Yes. I didn't actually, not better. I didn't explain it at all. So what you the Lyapunov exponent was introduced for quantum systems by Larkin and Ovshinnikov 30 years ago or something like that. What you do is you normally can write the Lyapunov exponent as a Poisson bracket between what you have at time t and what you did at time 0. Now, because it's a kick. Now change the Poisson bracket by a commutator, as of course you always do, and then you have the expression of the Lyapunov exponent of Larkin and Ovshinnikov. Now, this was Larkin and Ovshinnikov in the, I don't know, 80s, I don't know, 70s, I don't know. Then, much later, Maldacena, Schenker, and Stanford showed that this Lyapunov exponent, so defined, has a bound. It cannot be divided by temperature. It cannot be larger than this. So quantum mechanics doesn't allow you to have a Lyapunov exponent that is larger than something. Okay, fine. But on top of it, all the models, black hole-y models, saturate that bound. So they are as chaotic as you can possibly have. This is mixed with, I don't know, scrambling properties of black hole. And honestly, what I know from this is from Scientific American. But these are properties that people who do black holes like to see in models of black holes.
So, can I understand this as saying that the energy levels of these models are as packed as possible?
That would be a good question. They are very packed. There is ground state, zero temperature entropy and all. I don't know. We are about to post an article where we give an intuitive feel of what that means. But people usually what they see is see the proof. The proof doesn't make you feel much wiser, honestly. It's an analytic continuation that you can follow step by step, but when you get to the 8th step, you say, yeah, okay, but I got to the 8th step. Yes, I agree, but you don't feel much wiser. So I don't know. With Silvia Papalardi, we're about to, in the next 3-4 days, post a paper where we try to give an intuitive feeling of what it means. So I believe that it is a consequence of the uncertainty principle, nothing else. We believe that. We wrote the paper to convince the people of that.
Thanks.
Okay, thanks again. I think, Jorge, we are a bit over time. We can move to Pierfrancesco. Then if anyone has some question in the break, can ask something maybe. But
Okay.
let's move to Pierfrancesco now.
Wait, stop share.
Thank you again. And Pierfrancesco starts sharing.
Yes, let me just take, I wanna take.
Okay, I will start introducing you. Next speaker is
Do you see my slide?
always from Paris, and again on glasses is Pierfrancesco Urbani from Saclay, which he will talk about isostatic locking and marginally stable gases. This is a series of work he made with many of our friends. Please go on, Pierfrancesco.
Yeah, do you see my slide?
Everything is perfect.
Okay, thank you. So first of all, thanks for the organization of the meeting and for giving me the space. So I'm going to discuss a set of works that I've been doing in the last couple of years with Silvio Franz and Antonio Sclocchi, that was a PhD student at Paris-Saclay, and now is at EPFL. So the framework I'm going to set is the following. So we are interested in to study properties of glasses at low temperatures that are not well understood. So those systems are kind of anomalous. The response is typically very jerky with a lot of avalanches and nonlinear excitations. And a popular approach is to try to understand the energy landscape of such systems. So what you do is that you typically take the total interaction potential between the degrees of freedom and look at the properties of local minima of the interaction potential. And then you try to identify low energy excitations and try to build a theory of them. So I'm going to focus on this spirit. And I'm going to focus on set of spheres that interact with a finite range repulsive interaction. So you have a cost function that can be written as a sum over all pairs of spheres of a cost function that depends on the gap between particles. So the gap is just the difference between the centers of the spheres minus the radius, the sum of the radii. And of course, if this variable is positive, it means that the spheres do not overlap. So you are below the jamming transition, what is called the jamming transition. Otherwise, if you are at high density, you will have spheres that are forced to overlap, and you will have couples of spheres for which this H is negative. So this setting can be used to model several soft matter systems ranging from granulars, colloids, foams, emulsions, and so on. So I'm going to focus to the properties of these systems above the jamming transition, where you may wonder what are the properties of the local minima. So in this case, of course, everything may depend on the cost function that you take. And then you have two popular choices. One where you take harmonic spheres. So spheres repel with a kind of Hookean potential. And then you can also take Hertzian spheres. That is something that people have considered. So what happens is that it is clear that as soon as the cost function V of H is convex at H equal to 0, if you take two spheres and you take them when they are barely touching, if you just apply a dipolar force, so you compress them, they will overlap. Essentially because as soon as they overlap, you can establish a force that is arbitrarily small because it can depend on the amount of overlap between the spheres. And in this case, people tried to characterize the Hessian of local minima of these systems. So they looked at the density of states, eigenvectors of the Hessian, and then they looked at the rheological properties. So what happens when you take the system and you strain it in some way? So how local minima are connected with one to the other. So what I'm going to do is to change a bit the perspective, and I try to take a kind of strange path. In which I ask myself, so what happens if I take V of H, that previously was considered to be convex here, and then now I change the shape, and I ask myself, what happens if it is concave? Okay, this is a kind of strange potential. One may argue if it has any relevant meaning for real systems. But from an intellectual point of view, at least one can ask how local minima look like if I do this change. So to me, this is still an open question. And of course, the problem is still well defined from an optimization point of view. So what we did is to do something that is in between. So we took the linear cost function. Okay, so this is a kind of marginal situation that separates a convex shape from a concave one. And in this case, you have a potential that is just this form. So if the spheres overlap, they repel with a constant force. That is just the slope of this potential. Okay. And actually, if you think about it, this cost function is not so weird after all, because people, for example, in machine learning have used it a lot, for example, to train support vector machine, and they gave it also a name. It's called the hinge loss. So, okay, so we started to study this problem, and the question is, how does a typical local minimum of linear spheres look like? So if you want to answer this question, what we did is that you can take your favorite minimization algorithm, let's say BFGS, gradient descent, your favorite routine in PyTorch, then you adapt it to this problem, and then you run it and see with your own eyes. And what you get is this. So here it's a configuration in a local minimum of this potential. So we have a system of polydisperse spheres. Actually, these are in 2 dimensions, but we also did 3 dimensions. And remarkably, what we find is that the spheres separate in kind of 2 clusters. So we have couples of spheres that just barely touch, and we call them contacts. So those spheres do not overlap at all, they just touch. And then there are couples of spheres that overlap. Okay, so these are in black. In black, there are the couples of spheres that overlap, and in red, we have the contacts. So why this is so? It is so, the reason is simple. So imagine that you have 2 spheres that just touch, and now you try to make them overlap. So if you want to make them overlap, you need to apply a force that is at least the slope of this potential. So here it's 1. So you need to apply a force that is at least 1. As soon as I apply a force that is smaller than 1, the 2 spheres will not be able to overlap. So here contacts can sustain a finite force. So this is a kind of threshold system in which you have that 2 spheres overlap only if they are forced above a certain threshold that is set by the slope of the potential. So once we saw this, we started to analyze the statistical properties of local minima. And the first thing that we look at is what is the number of contacts that we have in this contact network divided by the number of degrees of freedom. So this is something that is really important. And in particular, at jamming, this ratio is equal to 1. And what we see is that above jamming, this stays exactly equal to 1. So we get an isostatic system far away from jamming at finite energy density. Instead, if you look, for example, to the overlaps, they start from 0 at jamming, that is at 0.84 here, at packing fraction 0.84, and then it increases in some way. So essentially, the system, when you minimize the energy and you look to local minima, self-organizes into an isostatic critical state. And you can understand the necessity of contact forces from a purely geometrical reason, because if you take like a system of this kind, and if you admit that there are only forces that are equal to 1, if you want to impose a force balance on a sphere, you need to find very ordered geometrical configurations. Instead, if you allow for contacts that carry forces that are continuous between 0 and 1, you can easily find an amorphous configuration where you can enforce force balance. And then what we did is that we looked to the statistical properties, other statistical properties, and I will tell you why we looked at those properties. So in particular, we looked, for example, to the distribution of contact forces. So here is the PDF. So of course, they are defined only between 0 and 1. That is the maximal force above which you get an overlap. And close to the edges of the support of this PDF, we have 2 pseudo gaps with a critical exponents that is compatible to with this value. Okay, and to both edges we get roughly the same critical exponent, so it's the same. And we can look also at the properties of gaps here. Now gaps can take both positive and negative values because we are beyond jamming, so the spheres will overlap, so we have negative gaps. And again, we find a power law behavior. So this is what we find numerically. And here we have an exponent gamma that is very close to this value. Okay. And finally, what we can look at is the structure factor of the local connectivity in the contact network. So you may look at the fluctuations of local connectivity, and we find a structure factor that goes to 0 with Q, which means that we have an hyperuniform system. We get an hyperuniform system in the local connectivity. Okay, why this is interesting? So what we find essentially is that we get properties that are very close to what we get at jamming. So at jamming, you can show that hard spheres have contact forces that behaves this way when the force is small. Of course, for hard spheres, you don't have any bound for large forces, where essentially you can get, for example, force chains and so on. And you have, of course, small gaps, but you have only positive gaps. Here, the system is a bit richer, because we get that you cannot have arbitrarily large forces, so forces are bounded by 1, and you can have the distribution of gaps that is that gets a power law both at positive and negative gaps. And within our numerical precision, those critical exponents coincide with the one at jamming that take this value. So, so the system, in a sense, when you minimize the energy, locks automatically into an isostatic minimum that has exactly the same critical properties that you get for our spheres at jamming. So it's jamming critical in a whole phase instead of a point. So you don't need to fine tune anymore if you want to go to jamming. So, so we can develop a mean field theory to understand the exponents. So one way is to study our spheres, linear spheres in infinite dimensions, following the tools that are in this book. We took a different route because we didn't want to study the full phase diagram, but we wanted just to understand the properties of local minima. So we replaced the original optimization problem by a random one, in which we take random gaps instead of gaps of this form. And we take a cost function that is practically the same. It's a linear cost function. So this model is called the perceptron. And it was studied, precisely this version of the perceptron with linear cost function was studied by Meyer, Henkel, and Zippelius, who derived this phase diagram. So here you have two control parameters. Sigma is essentially a control parameter that is roughly the sum of the radii. It plays exactly the same role as the sum of the radii. And here we have alpha, that is essentially a density of constraints. It's like the density in the system. So below this blue line, the ground state of the Hamiltonian has 0 energy, and above it has positive energy. So above this line, we are in the jammed phase. And we find that, so those people found that the jammed phase can be divided in 2 regions, separated by a kind of topological trivialization transition. So above this region, you have many minima, the system is glassy, and you have replica symmetry breaking. And below, you have just one minimum. So they didn't study in full detail their RSB. They arrived to, like, let's say, one RSB step in the description of this phase. But actually, you need full RSB to understand what happens. That's what we did. And through full RSB, you can get the values of the exponents. So I'm gonna cut a long story short. So how do you get the exponents? Essentially, in the full RSB phase, you have 2 PDEs that arise. And one was written essentially by Parisi for the SK model. We can get it also in this case. And it's a PDE of the Hamilton-Jacobi-Bellman type, which means that you have a kind of underlying stochastic optimal control problem, to which you can associate a Fokker-Planck equation, which is written here. So if you know optimal control problem, I mean, and you are familiar with them, it's clear that when optimal control problems have a boundary condition that is like singularities, so essentially your control variable do not do anything for most of the time except close to the end, where you get a scaling regime, and in particular a boundary layer. So here we get exactly the same. And if you analyze the scaling behavior, you get the values of the exponents, and you can show that they coincide with the ones that appear at jamming. And actually, the scaling theory that we obtain is a kind of it's a more general step that includes the one that you can get at jamming that was derived in this paper. So why do we care about all those properties and all those exponents and so on? Because essentially those properties are the ones that are important if you want to understand the response of these systems. So the physics of these systems is entirely driven by those properties. So in particular, for example, you can take a packing of this kind. So this is a packing of linear spheres, and then you can imagine to inflate the spheres. So you start a compression protocol. And we didn't do it for spheres, but we used the simpler model, the perceptron that I was introducing before. And essentially, you can monitor, for example, the evolution of the diameter when you inflate the system as a function of the pressure. Okay. And what happens here is that the evolution of the diameter doesn't follow a smooth behavior, but you get a kind of devil's staircase because you start to get a lot of avalanches. And you clearly see that you have events in which you have very big avalanches. So we can characterize completely the statistical properties of those avalanches. We can show that they are power law distributed. We can compute the power law. But the important thing that I want to point out is that if you look to the typical scale in pressure in which you get an event that destabilizes the system, this takes this form. And the exponent beta is connected with the exponent theta that controls the statistical properties of contact forces. And if you compute it, you get a beta that is even larger than 1. So this system is extremely soft because as soon as you push it a bit, it will rearrange. Okay. So that's all. I just want to conclude with these things. So the first thing is that we saw is that linear spheres give rise to a kind of jamming critical phase, which means that jamming is not so special anymore. I mean, you do not need to fine-tune the system to go to jamming. The unjamming transition is anomalous. I didn't show, but we get anomalous critical exponents with respect to, for example, harmonic spheres. We can understand kind of the dynamics of contact forces, at least when the landscape is simple, through Karush-Kuhn-Tucker dynamics. That is a dynamics that you can write for constraint optimization problems. And we can generalize the physical picture to the case in which you take piecewise linear cost functions. So imagine that instead of taking just one ramp, you take 2 ramps or 3 ramps and so on. And you can show that all this picture generalizes to this case. Now, there are a lot of questions that are left. One is what happens if you take more generic potential, still concave. And the other thing is that it's connected to Jorge's talk, is what happens if we canonically quantize the model. And this is something that we are doing with Thibaut Weinburg and Antonio Sclocchi. So the thing is that if you take linear spheres, those systems are expected to be chaotic because you get avalanches. So if you take the system in phase space and give it 2 kicks that are very, whose difference is very small, the system will evolve on 2 different minima that are very far away. This is just because they undergo 2 avalanches. And of course, you can add the inertia to the system, and the system will give you a very chaotic system. And then the thing is, actually, you can show that the system is actually hyperbolic, and this is due to the pre-stress term. And now the question is, what happens when you switch on H bar? So when you do that, essentially, the pseudo gaps that we can characterize when H bar is 0, so in the local minima, they get cut off by H bar, by something that is of order H bar. And we think that this kind of generate automatically a bound to the Lyapunov exponent that Jorge was discussing. And one may wonder if this is the Lyapunov exponent for this system saturates the one that was derived by Maldacena, Schenker, and Stanford. So we are trying to do the computation in this model, so we will see. Thank you.
Thank you, Francesco. There is time for some short questions. Actually, I have one very you say you canonically quantize the model. You mean you canonically quantize with boson or Fermi?
We take the model, it's bosonic, so we take the model, we add p square over 2m, then you do usually canonical quantization.
Yeah, but you can make also Grassmann variable and make Fermi. But no,
exactly.
in this case, you boson and
no, we are trying to do the bosonic version.
Perfect. Thank you. And other question?
Yes, may I? Jorge?
Yes, sure.
No, I was wondering, okay, I see. And it's definitely promising about the result, but do you think you will be able to actually do the mean field quantization?
Okay, so I can, yes, I mean, the point is that this model, when you do the dynamical mean field theory, is not like SYK, so you don't have an exact expression for the self-energy.
Okay.
So it's more complicated, but there are other models for which you can compute the Lyapunov and you don't have an exact expression for the self-energy. For example, if you take like spin glasses with like totally asymmetric J's, there you still don't have an exact expression for the self-energy, yet you have an impurity problem that is written in terms just of correlation function. You don't have the response function. And there you can compute. This was done by Crisanti, or Sommers, and Sompoliski. So you get an impurity problem where you get a Schrödinger equation from which you derive the Lyapunov. So our strategy is to try to do this.
Okay. Thanks.
That's okay. We are really over time. If there is a quick question, we can take it. If not, let's thank again virtually both Jorge and Pierfrancesco, and
thank you.
See you after the break with another chairman. So, bye bye. La registrazione è bloccata?
No, Pasquale, credo che stiamo trasmettendo su live, su YouTube, e quindi automaticamente sì. Ecco il chairman, ecco un nuovo chairman, Beppe. Abbiamo un po' di tempo.
Okay, I just passed the words to the new chairman. Ciao Beppe. And...
Ecco,
sì, ciao Pasquale. Sì, avevo già salutato, ma non mi avete, ero mutato, mi ero automutato. Dicevo, Raffaella, mi direte voi quando iniziare?
Esattamente. Fra una decina di minuti possiamo...
Precisamente all'orario previsto, 15:50 del mio computer. Ok, vabbè, allora ci sentiamo tra un po'. Okay.
Sì, ora c'è il coffee break virtuale.
Sì. Il coffee break virtuale, ok. Vabbè, mutiamoci allora, va.
Beppe, tra un minuto possiamo iniziare.
Sì, sì, sì.
Ok.
Okay. Okay. Good afternoon to everybody. I'm Giuseppe Gonnella, will chair this last seminar session of this Italian Society of Statistical Physics. Okay. And okay, welcome to everyone to this session. Let me introduce the first talk of this session. And the speaker is Antonio Celani from Trieste, and the title of the talk is Gun with Wind, Learning How to Use Kites for Energy Harvesting. Please, Antonio.
Thank you, Beppe. So I hope you can see my screen. And so the subject of this talk, well, first of all, let me start by thanking the organizers for having me here. It's a pleasure to talk at this first meeting of the SIFS. So the subject of the talk is about how to extract energy from the atmosphere. So this is of course, atmosphere has a lot of energy in it. Most of it we appreciate in the worst situations. That is when this energy is unleashed upon us, such as in thunderstorms. But we can also take advantage of the energy that is present in the atmosphere and convert it for human purposes. And so probably the most widespread technology about harvesting energy from the atmosphere relies on wind turbines. However, wind turbines are big, they're heavy. It's very difficult to have them planted to any specific territory because of resistance by the inhabitants of the place. So they are quite expensive. And they are quite static. So once they're there, basically you have just do it for the wind to come. So the interest has been shifted over the past years towards different kinds of technology. And the kind of technology we will be interested in today goes under the name of airborne wind energy. And it collects a series of technologies, an ensemble of technologies in which there are flying objects, which might be kites or gliders or any other device like that. And the intent, as in the case of turbines, is to extract energy from the wind. Here I can show you a couple of examples. So these are actual companies that already have commercial products. So this Enerkite is a power ground station. Here you see that there is a kite attached by the bridles. You don't see them. And here there is a power generating unit. So the idea of this device is that when the wind blows, the kite is allowed to move out. Okay, so it's carried away by the wind. And then at some point, then it's just wound back to the initial situation. So this alternating behavior can be used to when it's connected to some device to generate electric power. It can be used to sustain the production of energy over relatively long times. On the right-hand side, you see a system which provides energy in two different ways. So at the same time, this kite is pulling the ship in the direction of the wind, and at the same time, it's also it can also act as a device like in the ground station that I showed in on the left. So the advantage of these technologies is that they are lightweight, they are very portable, so you can move them from one position to another. They don't require all the engineering needed to construct a large wind turbine. They can go very high, hundreds of meters of elevation. So the largest wind turbines now are about 120, but you can imagine just the sheer amount of material that you need to build a turbine with respect to the one that you need to build a kite. The one specific aspect, which is the most interesting part for me as a physicist, is that this system, since they are light and they are carried by the wind, they can be controlled. Okay, so it's possible to change the configuration of the kite while it's in flight by pulling the bridles, by controlling its orientation in space. And not only it can be controlled, but it has to be controlled, because otherwise it would be exposed to all kinds of wind gusts, and the extraction energy would be much less efficient. So there's a lot of dynamics, especially when the problem is coupled to the real situation, in which the atmosphere is typically, when it contains a lot of energy, the atmosphere is also extremely unstable and variable and unpredictable. So this is essentially the motivation of why to look into this problem as a physical problem. So there are not only these important motivations to study this, but there's also you can think of the problem of energy extraction, pretty much like in this example of kite surfing. So you can see there is the surfer is controlling the position of the kite through these bridles here, the bridles here. And you can see that it can reach significant speeds, over 50 kilometers per hour. So this is a sort of a small version of the energy extraction that I showed you earlier. So what are the basic physical ingredients of this phenomenon? Well, we can model it, and we actually will model it in the sequel as a problem in which there is some block that is attached to the ground, and it's connected by a long cable to a kite that is a wing-like object, which as such is subject to aerodynamic forces such as lift and drag, which depend on the geometrical properties of the kite, of course, but also on the dynamical properties and the relative velocity of the kite with respect to the wind. And these two forces, lift and drag, are the ones that pull the block in its direction. So the objective is to find out how to control the kite, so how to maneuver, how to pull the bridles in one direction or another, in order, for instance, to set a goal like maximizing the distance traveled in a given amount of time and in a given direction. Okay, so the goal is basically to travel as far as you can by exploiting the energy that is contained in the wind without adding additional power to your system. As such, when you look at this abstract version of the problem, this is a problem of optimal control of the dynamical system. You have an objective, you have some control, and you want to find the best way to use it. So mathematically speaking, no, sorry, just before that, a quick look at how you can actually control a kite. So there are basically two main ingredients. One is the angle of attack, that is the angle that this kite, which is depicted here, seen from the side, the angle that it makes with the wind, relative wind velocity. And there is the bank angle, which is the angle that it makes by inclination. So here, sort of, this is the bank angle, and this is the attack angle. Okay, so I hope you can see it on the screen. Like I was saying before, the basic idea is to formulate this problem as the problem of control of the dynamical system, in which you have a set of dynamical equations which describe the the movement of your system or mechanical system, and you have some variables here, which are your controls, which basically is the way that you act on the system by making it bank or change the angle of attack in our case. And the objective is to maximize some integral over time, over that given stretch of time, of some reward function, which might be, for instance, the speed in a given direction. And this, of course, depends on the configuration of the system at any given time and on the control. So the way to attack these problems is to write down the Hamilton-Jacobi-Bellman equation and to solve it possibly analytically or numerically. However, there are two big hurdles to this program. And the first hurdle is that in order to solve this problem, you need to know what the forces are. So you need to specify the dynamics of the system, which is contained in this F function here, and also the kind of objective, how it depends on your configuration and your controls. And this can be extremely complicated. As for instance, in the case at hand, this would require to know all the relevant variables that control the system, which in particular would mean understanding how turbulence influences the motion to predict basically the trajectory in the future given the knowledge of the system, which of course in such a situation is very complicated, both from the mechanical and aerodynamical point of view, and both from the point of view that the environment is turbulent and unpredictable. And moreover, a system like that is specified by a huge number of degrees of freedom, and you would have to control them all, to understand them all in order to complete this program. Of course, you can approximate your model and solve an approximate model of your motion, but in that case, your result of your optimization would be as good as the model that you're using, and therefore maybe it's just limited in performance. So what one would really like to do is to find out how to control a system, but without having this information about the underlying dynamics of the system as well, and the kind of response that the system gives to the system, to the kite. So the first question is, can one find this optimal control without relying on a model? And can one control the system even though one does not observe all the relevant degrees of freedom in the system? So fortunately enough, we don't have to invent anything in this case, because the answer to this question is already present in what is known as model-free reinforcement learning, which is a machine learning technique which explicitly addresses the problem of controlling a system without having much knowledge, much a priori knowledge about the system itself. So the key ideas are that the knowledge of the model is replaced with empirical data. So basically, trajectories and rewards are sampled rather than being planned or predicted on the basis of the knowledge of a model. And the second ingredient is that the partial observability of the system, so the fact that the system actually lives in a very high dimensional space, can be attacked by using techniques from functional approximation. Functional approximation itself can take different flavors. So you can approximate your target functions, your objectives, by means of linear approximations using features which are defined by the user, which have advantages and disadvantages. If you get on to understand what are the right features for your system, you can have a very good performance. And on top of that, you gain in explainability, because the system is very transparent in its inner workings. It's also typically easier to train, and the machine learning approach that you take, the algorithms that you use, have solid theoretical guarantees. Or you can use, you can leverage on the power of artificial neural networks to construct nonlinear approximators, which can have much more impressive performances. A priori don't depend on any input on domain knowledge from the user, but can be black box, data thirsty, and computation heavy. So there are advantages and disadvantages to this too. So here we focus on the problem of learning how to maneuver this kite by relying on a domain knowledge approach that is using linear features and using the fact that understanding the physics of the system gives us a good hint about what could be or could not be the relevant variables to control the system. So how does reinforcement learning work? So it's actually quite easy to explain the general concept behind this kind of algorithm. So I will take 1 minute to show you sort of a very crude pseudocode of how these algorithms actually work. So at the beginning, so one class of this algorithm, so reinforcement learning is much larger than that, but this is a representative example. So the idea is to start out with constructing an estimate of what you think will be the performance of your system, given a certain initial context, a certain initial configuration of the system, and a certain decision, a certain control taken at the initial time. And this is embedded into a function, Q function, which is a function of a high-dimensional space, the space of context and possible actions, but it's parameterized through a certain number of parameters, which are the weights. Again, it could be linear or it could be nonlinear. And then the idea is that there is a repeated interaction of the system with the environment. So there are many, many episodes, repeated attempts at flying, in this case, at using the kite to push yourself forward over several episodes. And within each episode, basically, there is a continuous interaction of the agent, the decision maker, with the environment. So basically, the surfer interacts with the environment by observing the context, so collecting information about the environment, which can be very simple or very complex, may include visual cues, etc. But in this case, we'll keep it as simple as possible. It takes some action according to some decision, which is based on this estimate of the long-term return. Okay, so this function Q expresses how much we can expect to gain in the long run. And therefore, by taking a sort of a soft max of this function, we can sort of guess what would be the most appropriate action for the current action based on our current knowledge. Once this action is taken, the system moves into a different configuration and a new context is observed, a reward is observed again, and all these things are totally the mechanism that generates these new states and rewards is not known to the agent, it just observes them. And combining this information, it constructs basically an error. There is a difference between what is observed and what was expected before, and uses this error to correct for the estimation. This process, when iterated, brings to a better estimate of what the long-term return is, which approaches as much as possible the true expectation, and at the same time an improvement of the policy if the softness of the maximum is sort of hardened with time. So it becomes increasingly greedy. Okay, so what we did is just we set ourselves to study how to train a kite surfer, a virtual kite surfer, in a domain which is given by a numerical simulation of the atmosphere. So here we have basically a chunk.
Antonio, 2 minutes. Antonio.
Yeah, fine, thanks. A chunk of the atmosphere, which is going at the speed of roughly from 10 to 50 meters per second. And then we immerse our kite surfer, our model, into this system. And in a nutshell, this is what we observe. You see that after training, after a relatively large number of episodes, we see that the performance, which is shown in these left panels, then levels up and obtains a relatively good performance. As you can see here, that this process can be quite difficult, and it requires a lot of tuning. But eventually, as you can see from the panel from the right, it consistently travels for distances up to 3 kilometers in every episode. And this is basically very close to the maximum amount that it can travel given the speeds and given the length of the episode. Okay, I will pass by on the details of how this is obtained to show you finally just a short movie of what do we get at the end. So this yellow square is meant to represent the surfer, which is moving in the x direction. And in blue, you see the trajectory of the kite, which tends to have this helical shaped turns, always turning in one direction in this case. And also the position of the kite is displaced to the left with respect to the surfer viewpoint, which is something that allows to obtain a faster average speed, which you can basically see here. The distances are in meters, and this means that it's basically moving around the 10 meters per second, which is a decent velocity given the parameters of the system. Okay, so this goes on and on, but I need to wrap up now. So next things down the line, like I said, there are other systems which are more apt for power production than just using it for kite surfing. One of these is this reel-in, reel-out system, and we are currently studying how this can work. And we are also exploring from the sort of computer science angle what artificial networks, neural networks can do to improve performance, both for reactive strategies in which we use deep Q-learning, and for memory-based strategies for which recurrent neural networks are the algorithms of choice for now. With that, I thank you for the attention.
Thank you, Antonio. Any short question? Are you able to use a kite, Antonio?
So we are planning to move to the real experiment soon.
Okay.
Not ready yet.
So, if not question, also because we have some delay, I will go to the second speaker of this session, who is Vittoria Sposini. And the title of the talk is The Random Diffusivity Approach for Diffusion in Heterogeneous Systems. Vittoria comes from the University of Vienna.
Yes, hello everyone. Can you hear me?
Yes.
Perfect. And I hope you can also see my screen now.
Yes, we see the screen, not the face, but the screen, yes, yeah.
Okay. So as mentioned, I come from the University of Vienna, but I actually just recently joined here with this European program. So what I'm going to present today is actually the work that I have been that I carried out during my doctoral studies at the University of Potsdam at the BAS Center for Applied Mathematics in Bilbao. And these works are in collaboration with these people that you see here at the bottom, whom I thank for their precious collaboration. So moving to the outline of the talk, my research focuses basically the mathematical modeling of anomalous diffusion. And in particular, today I'll talk about this class of processes, which is defined Brownian yet non-Gaussian diffusion. So I'll give you an idea of what that is and why do we actually talk about heterogeneity at all. And then I will move to the general approach that we use to model and analyze the systems, which is the random diffusivity approach. So let me just give you a general idea of why we are interested at all in this kind of systems. And the idea is that actually there is this kind of paper that came out like in 2009, which somehow brought to the attention this kind of systems, which show this behavior. So if we look at for instance, at the system on the left, we see that there is a nanotubes, and you have these green colloidal particles which diffuse along the nanotubes. And if we study their diffusive properties, you see that if you look at the mean square displacement, which is this plot B, it seems quite linear. So you would assume that actually these colloidal particles are just displacing Brownian motion. But then if we go and have a look at the displacement distribution, you see that especially at short times, which is, for instance, blue, green, and orange, you have a very strong non-Gaussianity. And this is actually a semi-logarithmic scale. This means that this is an exponential shape. So this is why these are defined Brownian yet non-Gaussian, or also Fickian yet non-Gaussian, if you wish. And what I want to stress is that this is quite a universal, dynamic that we observe. So here on the right, there is another system, which is actually a 3D system. You have an entangled network. You have a colloidal particle that diffuses along this network. And for a specific ratio of the mesh size and the diameter of the colloidal, you see that again we have a linear mean square displacement and yet a very strong non-Gaussianity. So after this paper came out, many more actually started to come up with this kind of behavior. And we know already, for instance, that in glass forming systems and in supercooled systems, non-Gaussianity is a well-known property, and there are indeed new actually papers which are coming out that discuss this Fickian yet non-Gaussian diffusion in this kind of systems as well. But there is also, for instance, if you look at the displacement of these nematodes, which are little worms, again you can really see that there is a large heterogeneity from one trajectory to the other, and indeed what they show is again a sort of Brownian yet non-Gaussian diffusion. And lastly, I would like to mention this experimental paper, which I think is very useful to introduce our mathematical approach. So if we start from here on the left, what you can see is that you have these lights. These are colloidal, colloidal particles which are diffusing. And what they do is that they create some kind of spherical obstacles, which are these spheres over here. And you can give them a sort of distribution in space. So they can be like very kind of homogeneously distributed in space, or they can be with some defects, or maybe they can be very random, more or less concentrated. And what you see is that indeed, when you change the distribution of the obstacles in the environment in which the particles are moving around, what you observe is that there is this non-Gaussianity which appears, and it seems to be kind of an exponential shape of the displacement distribution. So the main idea of our mathematical approach is that actually we have to take something like a Brownian motion kind of dynamics, which we describe through this overdamped Langevin equation on the top left, where C is just white Gaussian noise with delta correlation. And we want to introduce some kind of heterogeneity, which we can think as heterogeneity coming directly from the medium, but also from the characteristic of the tracers, as we saw, for instance, in the case of these little worms that were diffusing around. Or, of course, we can also have both. And the main idea is that we want to reproduce these two main features, so the linear mean square displacement in time, and a probability density function, which is exponential-like, and eventually can also actually show a crossover to Gaussian distribution, because this is what we see at long times in some systems. And what I'd like to actually tell you is that there is this random diffusivity approach, which actually helps us in doing so. Let us start from a very, very simple model that I define like kind of static random diffusivity model. You can think, for instance, of this kind of stochastic representation over here, where you have your x of g, which is just a standard Brownian motion with a Gaussian probability density function, but you introduce a random scale. So the square root of lambda is actually just a random scale. So lambda is an independent and non-negative random variable, which we assume here to be dimensionless. And from a physical point of view, we can actually think this kind of lambda as related to the diffusion coefficient. Indeed, we introduce like a kind of random diffusion coefficient, which is this curly d, and we have a scale which is d naught. And this means that we are introducing a distribution of diffusion coefficients that the particles can have. And then it is quite straightforward to show that the probability density function that is followed by this position over here is just given by this integral. So basically what you have is that you have your Gaussian distribution that comes from your initial underlying stochastic processes. But then what you have to do is that you have to weight over all possible diffusion coefficients. And we call this kind of model static because once you define a functional behavior of your probability density function through this integral, the functional behavior is the same at any time, so it doesn't change at all. And it is interesting to see that this kind of random scaling in front of the Gaussian process does not change at all the trend of the mean square displacement. It is quite straightforward just by taking the definition and by introducing the integral that we found from the probability density function to show that the mean square displacement of the newly defined process is just given by this linear trend over here, where now your diffusion coefficient is actually given by the average value of the distribution that you introduce. But at the same time, thanks to this kind of integral that we have over here, what you see is that we are really able to reproduce a non-Gaussian probability density function for the particle displacement. And in particular, if we define a sort of gamma distribution for your diffusion coefficient, what you see is that the displacement distribution of the particle indeed behaves in a way that shows an exponential tail. Now, what we know is that though this system seems to kind of work quite well, it is not able to reproduce an eventual crossover at long times to a final Gaussian distribution. And this is why this sort of dynamic random diffusivity models were introduced, which are related to what they are also called diffusing diffusivity models, if you've heard of them. And the main idea is that actually we have a set of coupled equations. We start again from an overdamped Langevin equation over here, which describes the position of your particle. And then what you do is that actually you introduce a diffusion coefficient that fluctuates in time. And this means that actually the diffusion coefficient itself is defined, the evolution of the diffusion coefficient itself is defined by a sort of stochastic equation. Here, just for the sake of simplicity, we actually define D as the square of Y. Y is just an auxiliary variable. In this way, we are sure that our diffusion coefficient is positive. And then we set a stochastic equation for this auxiliary variable Y. It's possible to show following different techniques like subordination approach or path integral approach that actually the probability density function of the particle position is given by this, let's call it subordination integral, where you have again a Gaussian distribution, which is then multiplied by this capital curly T, which is the probability density function of the process, which is basically the integral of the diffusion coefficient. So what you see over here is that what we have to do is that now we also have to introduce a kind of stochastic variable, a stochastic equation for your diffusion coefficient. And it is quite easy to do it if we assume that we have a stationary equation. Actually, you just set your probability density function for D. You define the one for Y, and then you somehow can obtain the drift term over here following this very simple step. And if you look, for instance, if you set a probability density function for your D, which is given by this kind of gamma distribution, you will see that the drift of your Y becomes just a linear drift. This means that actually this Y is just following an Oste-Uhlenbeck process, and basically your diffusion coefficient is given by a squared Oste-Uhlenbeck process. Again, when we are introducing this variability of the diffusion coefficient, what you see is that the mean square displacement of the particle position, again, is not quite affected by these fluctuations, in the sense that now the mean square displacement can be calculated, and it's given by this 2 times the average value of this tau, which is the integral of the diffusion coefficient. And if we assume stationarity, actually we can prove that this is exactly, again, the linear trend that we were expecting. So even though the mean square displacement does not seem to really be affected by this fluctuation of the diffusion coefficients, if you have a look actually at the probability density function of the particle distribution, what you see is that if we define as tau star the correlation, let's say the correlation time of your diffusivity dynamics, whenever we look at the system at a time scale which is shorter than this tau star, what we observe is actually this kind of behavior, which is what we found from the static random diffusivity model. So this is a really possible way to introduce non-Gaussianity. But then when we go to actually times which are longer than this time scale tau star, we go back to a final Gaussian distribution. So just to convince you that this all makes sense, we performed also some very simple Langevin dynamic simulations. And indeed, we recovered completely the linear trend of the mean square displacement. We recovered a probability density function of your position, which is fully consistent with the non-Gaussian distribution that you obtain from this integral, which is represented by the solid lines here. And also in the case for the dynamic random diffusivity model at very long times, indeed, we recovered this Gaussian distribution, which is given by the dashed line over here. As you can see, this kind of models are just able to reproduce the heterogeneity that you can have in the system by introducing fluctuation in the diffusion coefficient. And I want to stress that here we are introducing, we are kind of mapping heterogeneity that can be somehow in space into a dependency in time of the diffusion coefficient. And now I just also want to give you kind of an idea of which kind of statistical analysis we can perform starting from these models. A quite standard one is the first passage time statistics. We know that this is very interesting, for instance, to understand how long does it take for a particle to locate, let's say that the particle is this red dot over here, to locate a target, which is the blue one. And all these different patches represent somehow the heterogeneity that you may have in the system. And this target location is a very interesting, and classical problem, let's say. And of course, as you can see, you can have very direct trajectories that go from the particle directly to the target, but you can also have indirect ones that explore the whole space before reaching the target. To solve this problem, we start from this setup of equations, very standard. The particles start from x naught, and it wants to find this target, which is located at xt. And when it finds the target, it gets absorbed. And the quantities that we study are the survival probability, which is basically the integral of this probability that we find by solving this set of equation. And the first passage time density function, which is mathematically given by the negative derivative of the survival probability. And it's quite general results that you can find is very interesting. It's basically that the survival probability follows the exact same equations that we found for the displacement distribution. So basically, once you have the survival probability for Brownian motion, standard Brownian motion, for the specific set of equations that you want to solve, you can show that the survival probability for the random diffusivity model is given in the case of static random diffusivity model by means of this equation again, this integral over here, while in the case in which you have a dynamic random diffusivity model, you have this kind of equation over here. Coming more into, if you want an interpretation of it, this plot that we have at the top left shows a very interesting result. So let's focus just on the black line. This is we are in a one dimension in a semi-infinite domain, and the target is located at the origin. And the particle starts from the right of the origin. And the black line is the result you would expect for Brownian motion. So somehow this is the first passage time density function. And this is the result of Brownian motion, while this, let's say the green triangles or blue dots represent the results for our random diffusivity models. You can see that actually we have a higher value of the probability density function at very short first passage time. This means that this heterogeneity in the system can allow some of the particles to have a shorter, let's say a faster target location, while when you go to the average value, there seems not much is changing actually. And this is a very interesting result showing that heterogeneity can help in some case, for instance, reaction diffusion. So this could happen faster because of the heterogeneity in the system. I see that I only have 2 minutes. I also want just to give you a very general idea of another kind of analysis that we perform, which is what we call a single trajectory spectral analysis. So basically, in a standard way, what you usually do when you talk about power spectral density is that you take this quantity over here, where x is your particle, like the stochastic process defining the particle. You take this quantity and then you take the ensemble average and you set this capital T, which is the length of the trajectory, to infinity. Now, this is of course from, when you want to compare this with experimental data, it does not make much sense, because somehow Of course, you will always have a finite trajectory length, and often actually you don't have a fully statistical ensemble. So this is why this kind of analysis was performed just at the level of this quantity over here, which is defined at the single trajectory level and for finite observation times. And it is very interesting to see, just few results that we have here, is that actually this quantity already shows at the single trajectory level what is the behavior in the frequency domain of your stochastic process. What happens that you just have an additive random variable over here, and then you can actually study the distribution of this random variable, as we did here, for instance, for this random diffusivity model. So you see that somehow increasing the heterogeneity, meaning increasing the amplitude, like the fluctuations becomes broader and broader. This was just to give you a general idea of the kind of analysis that we did for this kind of processes. And to conclude, I would like just to mention that this kind of, even though this kind of Brownian non-Gaussian diffusion seems to be quite ubiquitous, and it seems to come up due to heterogeneity in the systems, and this random diffusivity approach seems to be a good effective model, like kind of a toy model to reproduce this behavior. And it can be maybe interesting to understand what is the role of these fluctuations, of this heterogeneity, when you want to perform some analysis in the systems you are studying. I want to stress out that the time scale at which the fluctuations happens is very important in understanding how to properly model your system, and this is why we introduce the static or dynamic models. And with this, I will just conclude. Thank you all for your attention. And I mentioned here in bold the papers that we published with me and collaborators, but I also introduced some other literature because I think this was, this is it has been a very active topic in the last years, and there is a lot of work going on. So if you're interested, please feel free to just check these references.
Okay. Thank you very much, Vittoria, for this very clear talk, and there is time for questions. Malte, please.
Yes, my question is the following, for curiosity. Did you ever try to look into the behavior of two-time correlators? You did single-time correlators, you worked them out very nicely. What about two-time correlators and aging behind?
Yeah, actually, this is a good question. This is something that we did not check. I really wouldn't know what to expect from that. So it's a good point. It's something that we did not check at all. We just checked one-time correlator. So thanks for pointing that out. I think that would be interesting to check. Thanks a lot.
Okay, you're welcome.
I would like to ask a question.
Please, Marco. Is
Piero?
Marco? Yeah.
No, Piero.
Okay, Piero, and then Marco.
Okay, I understand that probably you can also accommodate in this description situations in which, even though the second moment grows linearly like a normal Brownian motion, at the same time you have the higher moments grow with a different exponent. I mean, some kind of multi-diffusion. Is this possible within this approach or not?
Yes, exactly. So this is indeed what we observe. So even though somehow the mean square, the second moment behaves linearly, actually we observe some kind of stronger non-Gaussianity when you check like the fourth moment, for instance, or higher moments. Yes.
But it is not constant. It grows with time. The non-Gaussianity. This is the question.
Yes.
Okay.
Yes. Exactly.
Thank you.
Okay, Marco.
Yes. Is there a way to infer the trajectory of this diffusion constant just from the trajectory of the particle?
Sorry, again, what do you mean? Like to infer the?
Let's say you observe only the trajectory of the particle, but you want to understand the trajectory of the diffusion constant. Can you do that?
So let's say that if you have in this model, we assume that the diffusion constant is changing at each time. So I don't think it would really be possible to infer the trajectory of the diffusion. But you could try to, for instance, to kind of say that diffusion constant is maybe a jump process. So you could try to maybe infer the trajectory of a diffusion constant at a larger time scale, maybe, which can be an approximation of what you have. I don't know if this makes sense.
Okay, thank you.
Okay, I will stop here the questions. Thanks again, Victoria. And
thank you.
And I think we can go to Malte. Hi, Malte, how are you?
Okay, fine, thank you. Let me just share.
Yeah, and so
in principle we work.
Yeah, the title, you see the title there, metaconformal invariance.
Yeah.
Biased Ising model. The speaker is Malte and Henkel from the Université de Lorraine, Nancy in France. Please, Malte.
Okay. In primo loco, molto grazie per opportunità di parlare qui. The topic will be metaconformal invariance in biased Ising models. This is work done together with Stoimanov from Sofia. The motivation is a long-standing study, a quest into dynamic asymmetries in non-equilibrium dynamics, motivated by analogies and particularly tremendous success of two-dimensional conformal invariance at equilibrium phase transitions. And it's a natural question to ask, can one do something similar? Can you hope for something like this also in dynamics? An important notion then will be immediately the notion of the dynamic exponent, which will describe for us the different rescaling in time and space coordinates. Of course, in conformal invariance, which treat time and space equivalently, we must have this dynamic exponent equal to 1. And when we look into examples of infinitely time-space transformations, of course, conformal transformation in 1 + 1 dimension, described by a complex variable in time and space, comes to mind. And I shall not remind you here on all the tremendous successes, in particular in equilibrium critical phenomena, that there are classifications for scaling dimensions, for example, in the Ising model, and so on and so forth. For clarity, in what follows, I shall sometimes refer to this as orthoconformal transformations. Today, I'm interested in other examples of infinite dimensional time-space transformations. It's not Schrödinger-Virasoro, which has a meaning for kinetics, phase ordering kinetics out of equilibrium. I want to fix on a new class of time-space transformations called metaconformal transformations in one-space dimensions, which on first sight look very similar to orthoconformal ones, but there is a distinction. In orthoconformal transformation, the basic coordinates are light cone coordinates written here in complex space. The realization in metaconformal one is different because one of these coordinates is immediately the time, the other one is a conforming light cone coordinate. So it's only this one, as you can see here in this scheme. In the orthoconformal case, these coordinates are orthogonal. In the metaconformal case, they are not. So, at least in one space dimension, orthoconformal and metaconformal transformations refer to different representations of the same underlying Lie algebra. So, let's look at these transformations more explicitly. I write them here in the form of Lie algebra generators. You have two infinite families of generators here. And since it's a bit abstract, let me write you examples. We have both time and space translations. They are the same dilatations as in conformal invariance, orthoconformal invariance, I mean, but there's now a new kind of a generalized Galilei transformation. And I want to point out this is both different from these time-space rotations you would find in conformal invariance and the standard Galilei transformation you would, for example, find in the diffusion equation, free Schrödinger equation, the Schrödinger symmetry of that. On top of this, you can also have accelerations, which in Galilei or Schrödinger transformations do not exist. And we have this infinitesimal transformation. And then, of course, you see you have two parameters here, delta and gamma, which will characterize each scaling operator. The question is, how are these related to standard orthoconformal transformations? So first of all, I write you down here the commutator. It always closes. And you can also make the mapping onto the standard conformal ones. There you had the left moving and the right moving chiral generators. And actually, by decomposing the X and Y generators in this way, and you can explicitly write the corresponding realizations, you then find back the usual conformal transformation. That indeed shows again, it's just a different representation, but the invariant equation is now this one. It's no longer the Laplace equation, but it is an equation of ballistic transport. And then indeed you have a theorem that these metaconformal transformations send any solution of this equation to another solution. The other important difference is now that if you look, for example, at the two-point correlator, it is distinct from the orthoconformal form. The form is written here. And to illustrate it, let's look here into a scaling representation of this two-point function, where you have a scaling function depending on the space and time differences. In the orthoconformal case, that is a very well-known form, which is a green curve showing here. I show you the scaling function as a function of the scaling variable. The green curve is the orthoconformal curve, which, as you see, is rounded here at the origin. And the metaconformal one at the origin has a peak. Parameters are chosen such that asymptotically it is the same decay. So you see, indeed, they are different and have different properties. Now, since we know very well there are many examples with realized orthoconformal symmetries, can we find physical realizations of metaconformal symmetries? And that is the task I want to set for today. We already recognized two ingredients where to look for it. We should probably look into situations where we have a ballistic transport. So we should probably look at systems where some preferred spatial direction. And we should look for systems where we should find this kind of two-point correlator. Okay, let's go to an example where we are actually doing this. And let's consider the directed Glauber-Ising chain. So just as a reminder, when we look into the relaxation dynamics or model A dynamics of unbiased spin systems, you can do a quench from a disordered state to some temperature, say below Tc. That is the phase ordering, far from equilibrium. This typically has, in a very generic way, dynamic exponent equal to 2. And in physical aging, you could look at two-time correlators or two-time response functions, provided you go into the regime where both the waiting time and the observation time and also their difference are large with respect to microscopic reference time. And then indeed, the prediction is that the Schrödinger invariance has been tested in many cases. Good. In the same way, I now want to ask, can we find systems with a relaxation dynamics with a dynamic exponent which is 1 and not 2? And of course, in a way that is not simply orthoconformal symmetries. And then, of course, the question is, can you make such a thing? What are the symmetries? And the examples I want to look at is indeed the directed Glauber-Ising chain. So we take the following. We take a chain with sides, and on each side we put Ising spins up and down. And now we look at the rates, how I can change the orientation of this red spin, for example. The rate of the change will be influenced by its two nearest neighbors, here shown in green. And when we have a biased system, then, and in particular the two nearest neighbors are in opposite states, then indeed the bias will show up because the rate of flipping up will be different from the rate of flipping down, as you can see here. On the other hand, if the neighbors are in the same state, then there is no bias, and I get these reactions here. So you see this model will contain two parameters. It contains a bias, and it also contains the temperature, which I choose here to parameterize in terms of gamma. That is the same thing. So I have these two parameters which are there. And then, given these rates, I can write a master equation to define the dynamics in the standard way. Here now, because of the bias, detailed balance no longer holds, but we have global balance, which means that the equilibrium state, the non-equilibrium state from statistical mechanics, will still be a stationary solution of the master equation. And then, when we want to analyze what's happening, we can define a two-time correlator. So we take two spins at different positions, 0 arbitrarily fixed and n, and we take two different times. That is the two-time correlator. I could also take the 2 times equal, and then I have a single-time correlator. And now Given these expressions, I can then write down immediately in the standard way the equations of motion. First of all, for the single time correlator, that is the equation I find. It does not contain the bias, but it does contain a Lagrange multiplier in order to take into account this constraint when I take a spin on the same side. Because of this condition, this correlator always must be equal to 1. This will fix this Lagrange multiplier. And then on top of it, I then have the equation of motion for the two-time correlator. I actually introduce here the time difference. I write it this way: the derivative is altered with respect to the time difference. And then here you can see in this equation, indeed, the bias does disappear. So this is then the set of equations of motion written down, and we can now start to analyze it. Indeed, it's no surprise that it can be solved, even for non-vanishing bias. And it turns out, if you use a fully disordered initial state, short-range initial correlations, you indeed find a dynamic scaling regime, but that is the standard one with v equal to 2, nothing new. On the other hand, there's some contradictory indication. If you were to write the same model in 2 spatial dimensions, then indeed, numerical simulations show there is indeed a dynamic scaling regime with a dynamic exponent equal to 1. So how can we reconcile these two things? And in particular, is there a possibility to find a meta-conformal dynamic symmetry, not a Schrödinger symmetry, in the directed biased Glauber-Ising model? And again, as I said, we need to probably to look after 2 ingredients. We want this bias equation of motion, and we want to have this covariant two-time correlator. For large time, the waiting time should be dropping off. In order to see whether it's possible, we proceed now in several steps. The first analysis looks at infinite temperature, or gamma equal to 0, and then we do it in such a way that this product is nevertheless remain finite. And then I also make a spatial continuum limit, and I'm taking out this exponential factor. Then, if I insert this into the equation of motion, then I find in the continuum limit this equation of motion that conspicuously looks like this one. And so the solution can, of course, immediately written down in terms of this compact variable. And if I go to the case, I say, let's take waiting time equal to 0, then I can actually relate this, this number here to this initial number. And then we see one thing. In order to have a meta-conformal invariant, that is, in order to reproduce this correlator, we should probably require a long-range correlator initially with some exponent aleph, some more positive. And if we say so, then indeed we would obtain the expected form up to this exponential factor about which we still have to do something. So that is the first suggestion, that there may be something to be found. Now, can we find a meta-conformal dynamic symmetry indeed in the directed Glauber-Ising chain with long-range initial conditions? Again, now the next step will be we consider first waiting times equal to 0. We keep the temperature fixed, gamma somewhere between 0 and 1, wherever, we don't say anything more for the moment. And then we solve this equation of motion for the two-time correlator with waiting time equal to 0. And in Fourier space, here is a solution. Okay, we want to see, can we find a scaling regime with dynamic exponent 1? That is, we want to keep k times tau fixed. Then, for unbiased diffusion, we would have to fix this one, but that would mean we should look at momenta much larger now, where we are here. That is, the bias scaling regime will be a regime which is only occurring at much smaller momenta than we are used to from the diffusive scaling. Okay, maybe there's something hiding behind. Furthermore, we shall now admit the long-range correlator. Here it is. And then we say the following. Well, now this correlator, inserting this part here, that is the initial part. Now this cosine term will merely give us correction to scaling. And then I obtain this function here. The integral can be done. And okay, I indeed find the expected form I want for the correlator. Again, up to this exponential, which we regard for a moment. In the worst case, I could simply now set gamma equal to 1. So that two-time correlator has the form. But we do not really want to do it for s equal to 0. We rather want to do it for large waiting times, much larger than the microscopic time scales. So again, we do the same thing now for any s. We find the following with again the single time correlator. And we again look for a scaling regime with dynamic exponent equal to 1. Okay, but then we see if that initial correlator should be of this form, k to some power, times maybe something depending on s, then we would have succeeded, because then we could make the same argument which we were carrying out on this side, and we would be finding the expected form of the two-time correlator. So now the question is, can we actually make sure that we can find this form of the single-time correlator in Fourier space? Now let's recall this. The equation of motion is this one. So we do a Fourier transform, we do a Laplace transform. In Fourier Laplace space, the formal solution is looking this one, where we have now this Lagrange multiplier. And we still have to take into account this one. Okay, well, this is all nice and well. This is not so very intuitive. Not everybody is very much used to this. So in order to get some idea what this means, let me come back, first of all, to the case of fully disordered initial condition. And that is what I'm showing you here. We consider the spin-spin correlator equal time. I take the Laplace Fourier transform that is plotted here over against the momentum for several values of the Laplace parameter here. Here is very small and long times, short times. And okay, so we want to look at this, and you see we have two regimes, one horizontal regime, one regime decaying off. Also, now what is the expected scaling behavior? Well, in general, we would say for large time, there should be some characteristic length scales. We would expect that this correlator should have this form here. And furthermore, because Ising strings are hard, this scaling function should have a tip at the origin. This translates, this scaling expression translates into this scaling form, which is written here. And in particular here, for large case, we expect a Power law in one dimension, which would reproduce exactly this tip here. So that is indeed satisfied. And then also, we can then go for the scaling. So when we have scaling equal to 2, I take here the rescaled correlator, I take the rescaled argument, we see a very nice data collapse as it should be. Good. Now we do the same thing and introduce some long-range initial correlator for the biased case. With some Aleph here, we take Aleph equal to 1/4. And here again, I show you the correlator over against the momentum as before. And you see certain things remain, namely the Power law for large momenta, short distances. And here the horizontal part got replaced by something else, which is due to these initial correlators. So we have two new distinct regimes. The expected scaling behavior can now be this form. I expect a Power law. Then I find here another Power law, what you can see here. And then if you now try first of all the traditional scaling behavior with z equal to 2, you find, well, here it's a good scaling behavior, but here, mind you, that's a log scale. Things are actually not really colliding very well, and also here, they're not colliding very well. In this regime where we want to have it, yes, but otherwise it's not so good. On the other hand, if we try the scaling behavior with z equal to 1, then we see that in this region here, now for the very small momenta, much smaller momenta than before, that's a good scaling, and of course here it's failing miserably. So what we see here is evidence that we have indeed two distinct scaling regimes with different values of the dynamic exponent. Okay, now let's put back the mathematical equations. We had seen we have the exact solution of the equation of motion in Fourier Laplace space. We admit the long times correlator. Then from the constraint we had, we can find actually the behavior for the Lagrange multiplier in Laplace space. When we have gamma less than 1, that means positive temperature, that's the behavior we find. At 0 temperature, gamma equal to 1, that's the behavior we get. And that actually, if we compare this numerically, that is indeed also the numerical behavior what we obtain. And then So again, we look, what can we say about the scaling regime? What we have, v equal to 1, k will be fixed. Well, if we were to do this for gamma less than 1, non-vanishing temperature, there no long-range scalings persist. But at 0 temperature, when I put in the behavior, then we see the following. Either when Aleph is less than 1/2, then indeed this is a dominating term, and we indeed obtain the expected scaling behavior. When Aleph is larger than 1/2, that is no longer the case, and it is this term which is dominating, and I'm finding something else. So indeed, I find if this exponent Aleph tells us that we have sufficiently long-range correlations, then indeed we can confirm the meta-conformal form of the two-point correlator. And we also see that the dynamic exponent, depending on the chosen value of the initial correlators, is either 1 or 2. And that brings me to the conclusion.
Okay.
I remind you again on the various possible forms of time-space transformations. We focused here on the meta-conformal one in one dimension. We have seen that this is indeed a good candidate for dynamic symmetry in the directed Glauber-Ising chain at 0 temperature with long-range initial correlations. And so that is a new representation of the conformal groups. Of course, what remains to be done, which is in progress, find further examples, and this is work in progress. I hope to be able to report more on this soon. Thank you for your interest.
Thank you, Malte. There is not so much time for 2 short questions, if there are, please.
Okay. If there's no question, then I think since I'm the last speaker, I should probably say a word of gratitude. And I think we should all thank the organizers for having put into reality this very nice, very interesting, very stimulating workshop. It was, even from a distance, it was a great pleasure to attend. Although, of course, it's not a real thing. But I think thank you to you all for this very nice and very stimulating meeting.
Thank you, Malte. And you said something that I also wanted to say. So I really, as the chair of this last seminar session, I would really warmly thank the organizer for this very well organized conference. And I hope that it will be redone in Parma in a different way with all people there. So thank you again to all organizers. Okay, thank you. Thank you. And also thank you to the speaker of the last session. Bye-bye. Ciao.
Beppe, maybe you can say that we reconvene in 10 minutes, more or less, for the roundtable. Okay?
Okay. Yeah. So in 10 minutes, there is a roundtable discussion about machine learning and big data. I hope that you will remain connected, please.
Okay.
Bye-bye.
Bye-bye.
Buongiorno.
Ciao Riccardo.
Ciao Matteo.
Come va?
Grazie mille di aver mandato il link perché effettivamente non lo trovo da nessuna parte. Era nello spam.
Yes. È successo. Succede.
Sei l'unico, anche Martin Weigt ha subito la stessa sorte.
Anche anche io. Lo so, ce ne siamo accorti quando ha scritto ieri sera Riccardo, poi abbiamo rimandato il messaggio, ma è chissà perché. SIFS, Gmail, forse troppo dovremmo correggere.
No worries, risolto. Grazie mille dell'organizzazione, by the way. Exciting.
L'unico problema è che non vedo ancora comparire Martin, che ho sentito stamattina.
Vedo.
Vabbè, aspettiamo ancora.
Dove sei di bello, Riccardo?
Boston, appena tornato da un'America che si sta riaprendo. Voli in aereo, viaggi, roba da 2019. Finalmente un po' di structure, un po' di safety, quindi iniziamo a essere più confident. Ormai credo sia al 65% di vaccinazione. In Massachusetts credo 75%, una cosa del genere. How is Italy?
Italy is doing okay, I think. Well, now it's going down, but who knows what will happen in the fall.
Yeah. Tutte le varianti finora sembrano essere, dopo il double shot, under control, però bisogna scalare le vaccinazioni hyper fast.
Che vaccino hai fatto comunque?
America.
Yeah, Pfizer. Fair point.
Ok.
Martin is there. Okay.
Yes.
Ci sono.
Me?
No.
Martin, we didn't move since this morning. We are in the same position we had this morning.
But you know, I don't replace my computer several times a day in my lab. It's just in one position.
Eric, welcome.
Thank you.
Hi, Eric.
Hi. Ciao.
You don't look like a person in holiday, on holiday. You look like...
No, I just came back from this.
You're very professional.
Yeah.
Okay. So...
Dunque, io ho pensato che sarà qualcosa in italiano, no?
No.
No, il mio italiano non è abbastanza, ha un po'...
No, non è per il tuo italiano. Non è per il tuo italiano, che dovrebbe essere una conferenza internazionale, anche se mi sembra che tutti quelli collegati siano italiani in questo momento.
Infatti sì. Solamente per io non
Yeah, we are broadcasting on the YouTube channel of the SIFS, so...
Oh là là.
Ah, ok.
Who is going to listen.
Ciao Guido.
Ciao.
Pari Guido.
And Guido, both Caldarelli and Tiana. I can see both. That's a lot of people, eh? Fantastic.
Yeah.
This is fantastic. It would be impossible to arrange in Sweden.
So I wait for inputs from Raffaella.
You can start. I mean, in a few minutes, we can wait for 2 or 3 minutes and then start.
Okay. I mean, if you think about it, it's Friday afternoon, a wonderful day of summer. After 2 years of lockdown, we are still in front of the screen. I mean, it doesn't make a lot of sense, right?
Stop to talk about wonderful days. I'm still in Paris.
Not to speak of it, is Midsummer Eve in the Swedish calendar. Huh? Tomorrow is a national holiday, the most important in Sweden, namely Midsummer.
It's already past the Midsummer.
Yes, I mean, according to the calendar, but according to the holiday, it's this year, falls today. I know.
Hi, Stefano.
Hi, Stefano.
Is there.
Hello.
So if you, I mean, if you agree, we can have a kind of a first round of opinions, and then we can have some discussion. Okay.
Fine. Sure. Start with questions.
Yeah.
Sorry?
Is it supposed
to
be?
Start with some questions.
Don't worry.
It's better to have a question before expressing an opinion, no?
Yeah, I will take care of that.
Okay. So, live on YouTube. Oh. View stream on YouTube. Start with some questions.
Don't worry.
It's better to have a question before expressing an opinion, no? Sorry.
No, wait, I'll take care of that.
So Ricardo, you have the questions.
Yeah, I was just I'm just waiting to start. And as I introduce you, I also kind of explain the topic, and then very briefly, and then you will be, it's not really a specific question, it's an opinion about the field, right? So don't worry. And then we can enter into it. I would say, okay, Raffaella, can we start so that?
Yeah, yes, Ricardo, yes.
Okay, so welcome everybody to this, I think, last event, right, of the conference, and I'm very thankful to the participants, in particular Eric Aurell, who is a physicist working also on inference and biology, Martin Weigt, again working on similar topics, so the inference in biology, and then Fosca Giannotti, and she's a computer scientist working on a very important topic, which is explainability of the behavior of, say, machine learning devices. And I think this will be kind of strictly related to the issue that we are going to discuss. And then Riccardo Sabatini, who is a well-known data scientist, so our active guy, say, in the field. And okay, so the topic of today, the idea of having this roundtable came out from some discussion that we had in the organizing committee, because I think it is fair to say that we are all a bit kind of perplexed, in a sense, about the interplay between machine learning and scientific research. So which is the role of machine learning, which is the role that machine learning is playing in the way we do research today, and what can we foresee for the future. And so this kind of, how is the kind of the scientific method changing in some sense. So let me just say, rephrase this in a little bit more in detail. So it's clear that there's been a lot of progress in the last decade, and in particular in the context of supervised learning and reinforcement learning, I would say. And I think it is fair to say that even in 15 years ago, no one was able to predict such a rapid evolution of the field. So if you look at TED Talks of 2005, you don't find, TED Talks talking about the next revolution in machine learning. No, you don't find this, okay? So this came as a bit as a surprise for everybody, for all the communities. And we all know now, we all say that this is due to the abundance of data, to the fact that we had a lot of computer power to play with, and also to new algorithms. And I would like to say that in this respect, that some of the tools that we are using today really pose some very interesting challenges from a mathematical and conceptual point of view, because the fact that we have tools that learns in a regime which is highly overparameterized and by solving a highly non-convex optimization problem, which is the learning problem, is something very fascinating that goes beyond, say, what was expected according to statistical learning theory and also to non-convex optimization. So there's a lot to understand from a purely, mathematical or modeling point of view. In any case, this device, there was an empirical evolution of the field and a lot of unexpected results came out, like a lot of application. I would like to mention, for instance, natural language processing, which is a fantastic application that you use every day, I guess. But speech, images, application in medicine, across all fields essentially, all fields which use data for their activity. Now, more related to physics, I would say that there are already a lot of applications in quantum mechanics, in complex quantum systems, in studying new materials, and so on. I have been particularly fascinated by the recent progress in application of machine learning to PDEs, to the solution of partial differential equations. I think this is quite surprising as a result, in particular some recent progress that has been made in this field in which they use an unsupervised technique to actually accelerate the solution of PDEs. And then there's been application, again, all across all domains of physics, okay? But it's clear that machine learning, understanding how this device works is a problem per se, because in a sense empirical results have arrived before the theoretical understanding, and so there are a lot of open problems that we need to understand. So there is a lot of work to do in this direction, in understanding how current devices work, and also in designing new devices, because there are some issues that are still totally open. One is the issue of causality, how to use these devices to kind of identify some causation patterns in the data, which is highly non-trivial, of course, result. Is a fantastic problem, in fact. But also improving performance in unsupervised learning is of great relevance, because data are essentially unsupervised. And the progress that we have witnessed in the context of supervised learning is much more pronounced with respect to the progress we have observed in unsupervised learning. So let me say that these are objective for the near future, but also we need to understand a lot of problems concerning how the current device work, how the learning mechanism functions. And here I think there's a lot of physics that enters into the game, because as I said, we are dealing with non-convex optimization problems, so kind of complicated energy functions, and in a very high dimensional space, in an over-parameterized regime. And we know very well that these devices, the algorithms that are at work are kind of behave in a, say, non-conventional manner. They are not just stochastic process that satisfy detailed balance. So there's something more going on here. There's a lot of out of equilibrium physics actually happening. So I think there's really a lot of work to do, and it's very exciting, and probably there are new things to understand. And also I should mention that this is of course, it's more a personal opinion, but I think that there's been a little progress compared to other results at the interface between machine learning and computational neuroscience. Still, we are in a sense, the two fields are not yet intersecting as they should. And so, again, also this is a direction in which possibly in the near future, we are going to hopefully to see some results. Now, one of the challenges that we need to face when we talk about machine learning is the challenge of so-called explainability. And Fosca is an expert in this. She also has an ERC currently going on exactly on this topic. And the explainability is something which Fosca is going to talk about it in detail, so I don't want to anticipate anything, but it's strictly related to understanding, to causality, and to many of the topics that I've mentioned. So in a nutshell, it's probably fair to say that compared to, say, 15 years ago, now we have a kind of a new tool, at least we use it a lot in research, and so a new tool to analyze big data. And this is really becoming, an everyday tool for all of us. And the consequences, of what, so this is affecting the way we do research. And I think it's kind of very interesting to understand, where this is going to lead us. And I think that, the latest result that we have observed, the latest of 2020, namely the result of AlphaFold, must have surprised most of you. So the idea that all of a sudden these guys of DeepMind came up with an algorithm that could reach a precision of prediction which is comparable to experiments, solving in some sense, and Martin and Eric are going to comment, I guess, about this, a problem that was open since 50 years, on which a lot of people have been working. It's really something astonishing. So, of course, this AlphaFold doesn't solve the protein folding problem, it doesn't explain everything, but at least it explains something. So these are so the consequences of these new tools are kind of very deep. So if you agree, I would like to hear from all of you, which is your perspective, in 5-10 minutes, which is your perspective on this problem on the future of research and machine learning, which you consider to be the most urgent problems and limitations, or whatever comes to your mind. I think it's a very open discussion we can have today, and I think that also questions from all the other participants are kind of welcome. So we can follow any order, and so Fosca, do you want to start and tell us the computer science point of view?
I don't know. So I agree with all the things that you say, that we are living a fantastic moment, really, where we have new tools that provide a sort of new microscope on things. Personally, I think that it's not only machine learning what is really changing, which is in these years, which has been changing the scientific method, but it's also data. So data which are not there collected to prove a theory, but data which are sprouting everywhere, like mushrooms. They are not always functional to specific or statistical, scientific or statistical research, but give a new point of observation at the very fine grain of complex phenomena. And then the wide repertoire of data science, of course, including machine learning, but also network science, statistics, provide this opportunity to scrutinize the such complexity. And this is changing, revolutionizing science, I mean, all sciences. And so what? Shall we put the scientific method in the attic? There was I don't know, in 2003, you know that Chris Anderson, which was the former editor-in-chief of Weigt magazine, he said, the end of theory, the data deluge make the scientific method obsolete. There was a sort of provocative article where he was saying, okay, now the data, and we don't need anymore any theory. Actually, I think that why we are living so that exciting matter is that there is a sort of a new tool, this which Jim Gray in the 2007, another computer scientist of 2007, named it the fourth paradigm. So the fact that we have the opportunity of theories and models and bottom-up discovery from knowledge may mutually support. A sort of we are sort of living in a sort of model of models. So we are mechanicistic models which can be challenged and falsified by as the scientific method wants, falsified by evidence which emerge from data, by new patterns which may help in changing, in providing new models. For my experience, this has been particularly true in mobility. So the last 20 years, all the mobility theories and the models of mobility have been challenged by the new data proxy, like mobile phone or GPS trajectory. And there has been an increasing production of new models for human mobility. And with this, so the data, the patterns from the data demonstrated that some previous models we didn't accommodate such new behaviors, and new models have been produced. So I think this is, and of course there are, so it's data science help in generating hypotheses, and then of course there are correlations, so there are problems of bias, causality, uncertainty. So the methods there have really to be very, very rigorous. So, but and my interest is the fact that we don't need, so science do not need oracles. We need a machine that generate hypotheses, machine to think, that help scientists to in falsification theories and understand. So that's why I think that we have to be a little bit cautious with black box models. We need to really have models which really help to explain such the form of the inference which has been done. So so I have this idea of explanation. I tell you what is my theory is the explanation. It's the Dr. House model essentially. So I see that the machine learning models are a sort of intelligent agents which are capable of interacting with a person, explaining and being capable of explaining and understanding each other, transforming the inference in something which is comprehensible to humans, and then the humans can take further decisions. That's why I think that explainability is an important break of this building the bridge between, I mean, at least for science, surely, building the bridge between this fantastic, I agree with Professor Zecchina, with Riccardo, that I mean, the new deep learning optimization framework, it's really fascinating, and also it's fascinating going up in the latent space and the reasoning on this latent space, and also it's really fantastic. But then at the end, it has to produce something which help the user. Let me use this computer science vision to explain, and also the scientists, particularly the scientists. Otherwise, I mean, we will not be helpful. So I think that the scientific method, in conclusion, is it's changed, but it's changed positively with really having a new tool to combine models together. But it is important that we put also there the capability of being very transparent to what we are doing, what the system is doing.
Thank you, Fosca. So I follow my screen order. So I would kind of ask Eric if you want to comment about this general framework. I know you always have strong opinions.
I hope that they are well grounded if they are strong. So my experience in this field is in the application which Professor Zecchina mentioned in his introduction, namely given by sets of biological sequences such as, for instance, sets of similar proteins, or as you say in biophysics, homologous proteins, but can also be other kinds of sequences, to use them to use machine learning on these sequences to infer some properties. And the recent great success is, of course, AlphaFold, which was a revolution and is an ongoing revolution. I was mainly involved in the work which came before AlphaFold, which was also revolution, but from a lower stage, in the class of models known as direct coupling analysis, invented by Martin. And the main review is backed by Ricardo, although he doesn't call it direct coupling analysis. He calls it inverse Ising problem, but it's the same technique. So these are, from the machine learning and AI point of view, quite simple things. It's parameter fitting in models of the exponential type. So for physicists, these are the models of equilibrium statistical mechanics. They are over-parameterized, and there are many issues in how to do this well, but still it is a much, much simpler framework in the modeling complexity point of view than what is implied in deep learning and similar things. So if I'm allowed to speak only from those things, which are the ones I know about DCA, direct coupling analysis, what is it that you infer? The great success is to use it as a tool to infer amino acid contacts. That means spatial proximity between amino acid residues in a protein structure, when that structure is shared by a large set of homologous proteins. Or you can do it for RNA, or you can do things on the genome level for viruses and bacteria, which I have been involved in. And so why this coupling at all? Well, the reason must be that there is some fitness difference in the structure, and this fitness, this structure is encoded by the sequences. So you have a different proximity, different propensity to find yourself in different structures or versions of the structure, depending on the exact sequence. So what you're actually inferring is not really structure, you're inferring synergistic components to fitness. The biological term then is epistasis. And it so happens that spatial structure in proteins is a very good proxy for epistasis. And this was known in biology a very long time ago. And it's in reviews well before actually the time when Ricardo mentioned. So in the beginning of the year 2000, epistasis from one protein is mainly an issue of structure. Now, to launch something, I think these methods, which are so simple that you can understand what sort of intuitively what they do, as a physicist is quite clear what kind of models they are. These inference methods and these AI methods on those problems, they work when the data is actually distributed according to those models. And this opens, I think, an important task for us theorists to explain why is it that data actually is distributed in that way. And there is no really simple explanation in general. You cannot refer to equilibrium statistical mechanics and maximum entropy arguments, because in fact, these are the snapshots from distributions what are necessarily non-equilibrium processes. There are some old results from Shakhnovich which are relevant in the context, and we have tried to leverage some other theories much more recently, which of course anybody can find on Google. But I think in the general point is to explain in physical terms why the distribution of the data is according to the models for which these methods have been proven to be successful. Thank you.
Thank you, Eric. So that's a very stimulating question. Riccardo, would you?
Yes.
Give your
pleasure.
Thank you.
Yeah. So I'm going to give maybe a quick example of how I see machine learning integrated in my activities. And again, I do drug design. And so there is a specific sub area, which is very interesting. And to me, tracks a little bit the story of the plus and minus of the machine learning world, which is generating small molecules. So drugs, we have today 2,000 small molecules approved in FDA. And the mathematical problem is very simple. So at the very beginning, I think 10 years ago, people started to ask a question: can I learn what a small molecule is in a statistical sense? So can I make a generator that spits out molecules that make at least the physical sense? We have a lot of molecules already built, and I expect that there must be a machine learning system to learn from a huge list of smile strings, which is a standard way to encode in molecules, and I will do chemistry generation. Well, the first generation of this algorithm were ridiculous. Like 80% of the molecule generated in a statistical sense were making absolutely no physical sense. So the grammar of the smile string was respected, but what was generated were not even buildable molecules. So how the industry solved this problem is a pretty interesting one. We started to do more sophisticated models. We started to learn from graphs and not from the smile string code. And at the end, we started to embed some physics in these learners to constrain the generation algorithm over a scoring function that had an intrinsic understanding of the problem, not a statistical one. So I generated a lot of potential graphs. A molecule is a multi-parted graph. Just out of curiosity, with 8 atoms, you do in the vast majority of drugs that are today approved. So I built this multi-parted graph in a statistical sense, driven by a learning of a library, but I still need a physical solver at the end to understand if this is at least making sense on a physical perspective. Like, can I build this molecule or not? So we haven't yet reached a statistical generation of molecules that is fully unbounded without a scoring that has at least a component of physics inside. The next generation problem, which is even more relevant, is can I build a small molecule that have a specific feature, like that binds on a target or that modulates a protein? And this way is a supervised problem. So you typically start with screening of biological assay. You come up with gigantic databases that have molecules on one side and your fitness function on the other, whatever fitness function, binding affinity, water solubility, you name it. And now the biggest challenge in the industry is, can we generate a new molecule that, on top of having to be meaningful and buildable by physical law, has also have a fitness function, so a scoring function that is relevant for a drug. So that is enhancing this binding pocket. So this is the world of chemistry generation. That is a subdomain of protein generation or understanding, but it's very, let's say, exciting. And at this level, at this point, we run it constantly, every day. Lots of tricks came out in the last years, and some potential breakthroughs, like graph convolutional neural nets, very complex learning system of adversarials. But at the end, when you run these models, there are 2 fundamental problems that you see when you actually start to put them in production. Number one, the bound learning of the problem. So typically, libraries that you use to score and to generate the training set are limited by how they've been assembled. So you're not exploring all the potential compound space, but you are very limited. And what comes out to be is that it's very hard to understand if the model is learning something beyond the limitation of the library that has been given, the garbage in, garbage out problems. This might sound a small problem that you can fit and you can solve by enlarging the amount of data, but this is where things really lie at the bottom, is that you never are in the situation when you can enlarge the training data ab infinitum. And you're always bound by a specific training data. And the model, what it learns, will always be bound by the statistical ensemble. Result is that many times when you request predictions from these models that are going far away in the new discovery of new molecules, the results are completely unreliable. And you have to take down one chemist, put it in front, or a ab initio model or a mechanicistic understanding of the problem to score out if this is meaningful or not. Are they useful? This model extremely useful. We are building exciting new research but the ability of this model to reach a fundamental mechanicistic understanding, to be reliable outside the training set that reaches the real ability of ab initio model, that's that missing gap that I think without mechanicistic constraints or without physics embedded in the learning, we will hardly reach by statistics. And that's also what at least AlphaFold managed. So it's a mix of statistical learning and physical constraint that enable the ability to go beyond just the learning part. And this embedding, it's still done by ab initio models, which are based on fundamental understanding of mechanics. So that's the contrast and tension between statistical learning and ab initio learning, for which I think ab initio and mechanicistic learning is still essential to rule out some naive and crucial problems that statistical learning has. I hope I summarize one example and we can deep dive a bit more.
Okay, very, very stimulating. Thank you very much. So Martin, it's your turn.
That's to be complicated to add, but maybe I go back to a bit to the point of view of data, because what my experience is not really an experience which is asking any fundamental questions in learning, machine learning, statistical learning, and so on, but it's more the application of approaches to get information out of data. And if you look in biology, I'm working a lot on sequence data, and sequence data are something which came up. There was a revolution in 2007 with next generation sequencing, where suddenly sequencing became something which is very cheap and is very achievable, and people started to sequence like hell. And ever since, the amount of available sequence data has been growing exponentially. What's coming out of these experiments is sequences. So that's strings of letters, and that's it. And you can, with biological knowledge, you can, out of these sequences, which are DNA sequences, you can read out protein, probable protein sequences, and so on, but it's still just strings of letters. And then there is obviously a lot of biological work which has been spent on accumulating some knowledge about proteins. So this is basically what would be the input to anything like supervised learning. So you put labels on these. So for instance, you determine structures. That's what is the input for AlphaFold, for instance, or you determine functions and so on. But the amount of sequences which have such experimental labels, because these labels to get is super complicated. It's experimental work, it's human labor, protein by protein, is something like 500,000 sequences have these assignments out of 200 million known sequences. So that's 0.2%, I think, if I do write the math. So we are in a situation where actually we have many unlabeled data and relatively few labeled data. Enough labeled data, for instance, that people like those of AlphaFold and DeepMind managed to do something which is totally incredible and was not expected even 2 years back they could do so rapidly. So people expected this something to be for the next decade at best, is to for many of these sequences where we do not have the label, where we do not know the structure, to make predictions which are basically as good as experiments. And they did this because they did some very intensive learning based on all experimental data and all sequence data which are available. So but still this is prediction and not really understanding. And I want to illustrate this in a very simple example. If you take a protein and you do a few random mutations on this protein, You will destroy the protein. The protein will unfold, it will get destabilized. But if you give that protein to AlphaFold, it will give you a very nice structure. And why will it give you a structure? Because you have learned on many folding proteins, you know their structure, and you learned how to go from the sequence to the structure, conditioned to that all your input was nice proteins. Now, if you give a bad protein, it will give you a nice structure. And actually understanding mutational effects and why proteins do not fold or predicting the stability is remaining a very big open problem in protein biology. So, and this AlphaFold just by construction cannot provide. Another point which I would and it's important question. So that's something where one has to look, one has to see how can we get this out of the data we have. And then another point I would like to do, Ricardo has told about, let's say, the unsupervised learning lagging behind supervised learning. But I told you that in this protein data, only 0.2% of all sequences have some labels, have some annotations. And then there is this enormous amount and exploding amount of data which is there, which is without labels, and which have a rich structure, because every single sequence in there is a sequence which folds, which is a nice protein, which folds, which makes some function in some organism and so on. And in this case, unsupervised methods, and sometimes very simple, from the machine learning point, very simple unsupervised methods, like what Eric was talking about, but also sometimes more complicated methods. And those, they can extract a lot of information just from the organization. But again, that's not yet understanding. And if you, to connect the behavior, so or what the parameters of these models, they have a lot of parameters typically, even the simplest ones, to connect them to something which is the physics, the biology, the chemistry underlying them. That's a highly non-trivial question, taking to many smart people a lot of time, advancing much slower than many of the more prediction-related applications, but I think still a very important scientific question, because at the end it's about understanding.
So thank you very much. It was a very interesting round of opinions. So maybe I'll just ask another question. Then if everybody wants to, I have a couple of questions I want to ask just to follow up on what you have just said. One thing is, well, first of all, it's a provocative question. I mean, now what AlphaFold is doing looks totally obvious, right? Say they take the data, put constraint, but 2 months ahead of their announcement, you would have not been able to predict.
The 2 months ahead, yes.
Okay, 3 months ahead.
And the year before.
There were some rumors circulating. There were some rumors circulating, but
okay. But I mean, keep in mind that so there's something happening which goes sometimes beyond our imagination. I think that here we have a problem, and namely we have the problem that a lot of this research is done in private companies that do not share information. I see this as a very big problem in perspective, and so I want to just point out this as just a quick argument of discussion. And then another more fundamental question is that, so we are talking about understanding models from this machine learning device. In a sense, it's like explainability. But it seems that the computational scheme, which is arising from this overparameterized system, is a scheme in which you should not pretend to interpret the single parameters as telling you something about how the system, the mechanistic behavior of the system. I mean, it's very different from, let's say, what you and Eric have been doing in the context of proteins, in which you use a model and you really interpret somehow, you disentangle directed and undirected correlation and so on, and you give a meaning, let's say, to the parameters. In general, when you have these huge networks, and let me remind you that GPT-3, the network for natural language processing, has 180 billion parameters. So it's like saying that essentially it's doing computation in a totally different way, and we should not pretend to interpret the single parameters, but have a more fundamental approach, thinking that the kind of computation that is done uses a different paradigm in a sense. So we should think more about what it means to understand. And so I would like to ask you, on the one hand, what do you think about the fact that information is not shared, and it's becoming more and more difficult to reproduce the results, and on the other hand, what does it mean really to understand? And maybe also Fosca would like to tell us a little bit more about what explainability means exactly in computer science. So these are just two questions that I thought we could try to address, and just feel free to raise your hand.
If you want, I can start. I mean, actually, you made like 10 questions, not 2 questions. So first, let me first say that I appreciate very much the examples from specific contexts, because it's true, and this is confirming what I was trying to say before. So it's not only supervised, but it's also unsupervised important tools for understanding some component, but then you have to insert this within some more sophisticated models. So really, I strongly believe in this data science as a model of models, so we have still to go to the next level. So where those two, the various set of models can really be combined, and ideally we should have a way to combine them. So that's one argument that came up when you were before. So coming back to the fact of not sharing. So, and that's another important problem, because and it's the reason why there is a lot of push of open science. And so I mean, if you look, for example, what happened with the COVID, with the pandemic situation. So at the beginning, so there was a lot of collaboration among scientists, and then that was also the reasons why in 1 year we arrived to having a vaccine. So the shortest one was rubella, I don't know, or another sign that was 3 years. That was done in 3 years, and then 1 year we managed, and that was due particularly by thanks to the sharing of information among science. But it is a very complex story. Of course, when you have AI models, which are, I mean, particularly supervised models, which are, so there is a problem of trust of the AI model that we use. If we don't have any information about the training set which has been used for train that model, if it's completely opaque because there is some business behind this, maybe very difficult to trust it, or you trust completely. So that means that the users simply demand completely to the AI the decisions. Otherwise, at the end, they will not trust. So I think that we were one important thing will be to set up pipeline for the design of such a model, for which all the steps, the very complex steps of constructing an AI model are very transparent. Also, when they are, there is a business behind. So at least if you want to use in some high-stakes scenario, so there has to be some responsibility behind this. So, and then there has to be a point, a place where, if it is needed, someone has to go there and observe what is how the data were done. But I think that so explainability means also this accountability part. So having also the transparency on all the steps of the pipeline, which provide the construction that is below construction of an AI model. And then let me say, I'll try to say in 2 minutes, sorry for being so long, to what is explainability so far, what is the research on explainability so far. So what is trying to do the research is there are 2 main lines. One is changing the machine learning, the inference model. So essentially going towards a transparent machine learning. That means that in some sense, the learning process has to be coupled with some semantics. Of course, it is difficult to do it generally. For example, there are some researchers which are using a mechanicistic model in some point. There are other approaches that are using knowledge graph, such that at each layer of the inference process, some semantics remains attached that can be at the end reconstructed for the purpose of explainability. So, but we are still at the very beginning of this story. So going towards completely transparent models. That means that at the end, the model that you have, it's explainable by itself. The other approach is the post-hoc explanation. So we stay there are black box, you stay with the black box, but they are allowed to be audited. And then you construct explainers, just observing the input-output behavior of the black box model. And then you use so the entire pipeline, it's so you have a training, so you train a model, and also you produce an explainer, which can work as a post-hoc explanation. So those are the 2 big lines, and there is a lot of proposals around this. So, and then we go from explanations that are simply features relevance, to explanations as argumentation, explanation as a conversations. So there is really a wide variety of research. Sorry if I was too long, but
no, it's fine. So, do you want to comment, Riccardo, Eric, or Martin, about?
Yeah, I have a couple of things, and I mean, very stimulating conversation. So chop me if I take too long. But so I'm part of on the data sharing and code sharing. I think things are intertwined. So I'm one of the members of the Global Partnership of Artificial Intelligence, which is a large multi-stakeholder group of the United Nations. And one of the groups that I'm part of is exactly speaking about how industry can share and can enable more sharing. And so there will be a report coming out for the next year. I think is a great effort with a lot of different experts. But putting back the head of my own opinions here. So there are 2 different aspects. So on one side, if you really look at the industry is sharing a lot of things in the code domain. So we have a tons of code that is shared by the industry. TensorFlow, PyTorch, you name it, like hundreds of millions of value of top-notch code development is shared for free constantly. So from simple scripts to libraries and so on and so forth. And if you remember back in the days, that was not the case. So when you had the good old fluidodynamic solvers or codes that were running ab initio, code was not shared in this way. Now, today we share code, but we don't share one fundamental part, which is the data. So the ability to train that code to be able to solve a problem. There are 2 different layers. One is privacy and all sorts of legal problems, which is interesting, but it's not very scientifically relevant. It's still extremely relevant from a societal perspective. But on a scientific of problems are defined by the training set to the point that the algorithm is a commodity. Like actually, we should share it all together because I can learn from the academia. I can do all sorts of things because in a statistical learning, the definition of the solution space lies inside the training set. And it's both a crucial problem that is existing in this type of learning that is not existing in the ab initio learning, where once you define and you understand the equation, finally, that is your secret sauce, and the data is for free. You can download 1,000,001 example data sets of proprietary code solvers because the secret sauce is in the solution, is in the intrinsic understanding of the solution. And so these are, I think, is this intertwine between we are in front of machines and let's say the type of learnings where the real secret sauce is and the real limitations and the real power is fundamentally lying in the training set. How to solve this on a scientific perspective, coming back to the example, is somehow trying to build these adversarial approaches where you have a machine that understands or that at least has been instructed by the mechanism of the problem, and a machine that tries to solve it statistically. So that you have a statistical learner that sometimes will spit out nonsensical thing, like a nicely crystallized protein that should not exist. And you have an ab initio or a human or a physical test that tells you, this is actually wrong. It makes absolutely no sense. So when we will move in this different domain, probably also the way we are sharing things will change. But things are really tied together. And today we are in the era of code is a commodity, training set is proprietary, because all the learning and all the results are lying inside that statistical domain of the training set. It's a very interesting one, but Martin, go ahead, sorry.
May I ask you a question on this? Because in the case of AlphaFold, I think it's the situation is in a sense a bit different, because much of the training data is actually publicly available data, because it's multiple sequence alignments, it's structures which are deposited in the PDB. Elaborating them to make it a nice training set is still a lot of work, but in principle, the data is there. Whereas up to now, as far as I know, if nothing changed in the last hours, we don't really know what AlphaFold 2 in terms of architecture of the network and so really did. We know they did some end-to-end learning. They start with sequences and they spit out structure, but what in the middle is really happening, we don't know.
Even they do not know.
What is really happening, they don't know, but at least they have a code which is working, and so
exactly.
And that's why the code that's why the code is proprietary. I think that's where
in the case of AlphaFold 1, it was still a bit different, because they used more or less the same strategy as which was used by the academic research in the same period, but they did it slightly better. That's why the gain was limited, but was nice gain, but was limited. And people with the little information which was immediately there, people in academic research were able within few months to get to the same precision. Now it seems to be different to me. And there actually the code is what is missing for the moment.
Yeah, and I agree. That's why if the secret is somehow in the training set, you're happy to share the code. But if the secret sauce is in the code, you will hardly see the code before a lot of corporate infrastructure to make sure that there are the right check and balances to share it. My feeling is that in AlphaFold, and again, they, as you mentioned, they presented results in 2 competitions. There's been a nice understanding of what was the generation 1. My feeling is that AlphaFold is using a lot of, or in some integrations, a lot of physics and a lot of ab initio reductions to support the learner to converge somewhere. But again, we don't know, and I feel that is the domain where the code and the solution is becoming the secret sauce, and the data is available. While many machine learning, the data is the secret sauce and the code is for free online.
Eric, would you like to add something? Or?
Sure. lots of things as already said. So AlphaFold 2, we don't know what it's doing, but AlphaFold 1, we know partly at least what it's doing. And I think it should be emphasized also that they did better engineering than the academics had done before. And that's something that's, of course, is well known in software industry, that if you have a structure in making better code, you can actually produce better code than the researchers can do, at least for some cases. And it's not that they were always better than everybody else. It was just that they were consistently or more consistently better. It's not that in AlphaFold 1, they were able to produce results that had never been seen before. It is that they were able to do it much more often. Martin can qualify or say if I'm wrong. I mean, he knows this result very much better. So I don't think we should really be so surprised from this. Industry has different incentives in quality control, in follow-up, in documentation, and in actually producing stuff that works. Well, if you build a machine in industry and you sell it for money, you're expected to work every time and to be of high quality. And if you have a research grade product, it's not the same thing. So that is an underappreciated part of the story. Now, what AlphaFold 2 actually does is quite possible that it uses physical insight. It's also possible that it has better engineering again. I mean, we don't know for the moment, so it's hard to comment on that one. On interpretation and explainability, I would like to agree very strongly with what Fosca was saying, that it is our human society is geared to understanding which we can explain one of us to another one. And I think I can even find a quote by Niels Bohr explaining that this is what science is about. It's about, in the end, learning is about being able to explain one human to another one. But we have our legal system is made this way. Our political system, at least in Europe, is made this way. You're supposed to be able to explain one to another why you think something is true or should be done and not another one. So therefore, we are geared to, and the whole society and the way we interact with other people gives a great advantage to when you can explain something. And then also you can hold somebody responsible. And if you have a model which nobody understands, whose fault is it if it doesn't work or if it gives the wrong prediction? That you cannot sue anybody in a court of law for something that nobody understands. And I think this is going to be, for AI and for machine learning, is going to come back as a stumbling block. That's my own private conviction. Should I say something more?
Right. So maybe, I mean, there are a lot of questions that could be added, but I think that it would be nice if somebody from the audience would like to raise the hand and intervene and in some way ask question or just give a quick opinion about what has been said. It would be great. Otherwise, I can just proceed, but we don't have a lot of time, so it's good if you have. Roberto.
Just one word. First of all, I want to thank all of you. It's really a very nice roundtable. And I think that I am quite close to what Eric was saying in the last part of his speech, because I think as scientists, we have really some duties with respect to people. And explainability is really a very important issue that also has all the implications with ethics and other responsibilities that are on our shoulders with respect to the people, because we are the ones that are supposed to produce information, and we are supposed also to explain how we produce it and what is it for. So I think that I am astonished, as probably even more than Ricardo, about the recent achievements of machine learning and big data analysis and so on. I mean, it's obvious that we are facing a really impressive progress in this direction. On the other hand, as a community, we should be very careful. We have in the history a lot of examples that when we are too much, how to say, excited about something, we are not, we are able to produce some disaster sometimes. So, I mean, even as scientists, so we must be careful at any level. This is my very simple wording, because for instance, I don't like to discuss if metaphysics was over or theory was over. These questions do not really are of interest to me. My point is to understand what can we do, what we have progressed, in which direction. It's clear that statistical inference is going to become a very effective tool to be used for this kind of things, but I don't believe, this I want to say very firmly, that I don't believe that science is made by their data at all. I mean, it can be done with data, but it's not data. I have an historical example. If you go to the library of the Royal Society, you can see more than 60 volumes collecting all the data collected by Faraday. But Mr. Maxwell, who was not an artificial intelligence, was a natural intelligence, wrote his equations. If there is a way to use an algorithm to extract from the whole library of Faraday Maxwell equation, then I start to believe that data science is really the only science existing in the world.
Thank you, Roberto. Matteo.
Yeah, so thank you very much for a very interesting question. So I want to go back to this issue of that you raised at the beginning, Riccardo, concerning the convergence between data science, say, machine learning and systems neuroscience. Okay, so my impression is that there is a, I mean, the big question, I don't know whether you share this opinion, but the big question is that we don't really understand what it means to learn. So in the sense that once you define what it means to learn, I mean, what is the goal function, what is the data, what is the task, etc., then well, there is a well-defined, say, set of tools by which you can do supervised, unsupervised, even unsupervised learning. You always have to specify whether you want to do data clustering, how do you want your data to be represented. But this is not what life does, what the brain does. I mean, the brain doesn't need to just processes raw information. I mean, of course, the brain is a very complex machine, okay? And so you would say complex machine, I mean, learning is just a complex machine. And it's just a complex machine. But really, I mean, I think if we want to understand what is the connection between machine learning and, say, cognitive neuroscience, we have to try to address this issue of what does learning means. And I don't see the field going in this direction. I don't know what is your impression. Metaphysical, maybe, but I'll point.
So Riccardo, you want to?
I'll try to sketch a surely unsatisfactory answer because it's a pretty complex question. But I remember one quote. I can't recall exactly what was the paper. It says machine learning is still feeling very odd because you have to show an algorithm a bird 10,000 times before it will be able to classify a bird. And if you propose this task to a human being, at the fifth picture, you will be very surprised if it doesn't tell you that it's a bird. And there is this issue of one-shot learning and how we actually manage to go from a picture of a bird to understanding the concept of the bird and from transferring it across all sorts of media. We learn from a picture of a bird, we go out, we see a three-dimensional bird, we hear the sound, so we build the concept of a bird in an extremely fast way. So my feeling, and the only grasp that I probably encounter in my experience is one of the steps that we do in learning is always a stage of embedding. So we have to take some form of problem and embedding in a learnable process, in a learnable feature. So we compress reality in a vector that then we can throw to a machine. And that embedding, the more I notice complex problem, the more the embedding really plays a crucial role. Some of the biggest breakthroughs have been done when we nailed the right embedding. So pictures have a very natural embedding, and that's where we learn machines to train and to understand this. Molecules and graphs, there's been some fundamental breakthroughs on how to embed them, and that opened up tons of results. Audio, we are getting there, it's very complex 3D. But my feeling is that if I will point somewhere, is the compression ability of the brain to build almost a global embedding, highly interconnected, that then is enabled to be learned in a very efficient way. So I don't think the very secret, I mean, it's an amazing machine, whatever, everything is better in the brain. But if between the two steps, I would be very excited to understand the embedding function of the brain before the learning. Because if we get a great embedding, learning is much better. That's minimal answer.
Certainly also confirmed by, I mean, by this issue of overparameterization in a sense, right? So, which is difficult to interpret, and this connects with the fact that it's not always easy to interpret the parameters in terms of a physical phenomenon. Just think to the application to PDEs. I mean, instead of trying to solve them numerically, use a distributed system to make prediction. This is, you really use a different computational scheme to achieve the same objective. So there's something, I totally agree with you that the embedding and the representation is something new. I mean, something crucial. Matteo, maybe if I can just comment on your comment, is that you're making a huge jump. You want to go from machine learning to cognitive science. I would just stop at computational neuroscience. I would be happy just to find common question between machine learning and computational neuroscience. In a sense, I would like to see the metabolism of machine learning. I mean, like you have constraints on the device, you have energy constraints. So you really want to learn not by matrix multiplication on hundreds of thousands of GPUs and so on, but you want to learn with something which is constrained. And I think this is kind of, it's going to tell us a lot about, also fundamental mechanisms of learning. And so we have not been working a lot, I mean the community has not been working a lot in this direction because of the success of the, say, software approach. But possibly that's a field of intersection that needs to be developed in the future, some computational metabolism of machine learning. And maybe this leads to some overlap with computational neuroscience, not cognitive science. That's another level that I don't even dare to mention in this. So I don't, Martin, you have comments, or Eric, or somebody else wants to
I have a bad news for the one from the sorry, for your colleague that I don't remember the name from the public that said, so the bad news, if you give to a machine learning all those books, at the end he will, so you'll have the Maxwell equations. So that's the bad news. So,
sorry, can you repeat? You will have Maxwell equations?
Exactly. That's the bad news. We will not understand.
Sure? Really? Are you sure?
Yeah, I think so. First, and secondly, I think that the real challenge is what Riccardo says, is that I mean, it's a matter of how many data you give, and then you will have, and then, but the real challenge is we are learning. Humans do not need that many data for arriving to a concept, so a higher order concept, which is this set of pixels is a cat. So the real challenge will be learning from few data. But I'm
really astonished by that.
Yeah,
I don't see how an algorithm can think about the displacement current, because in the data it's extremely difficult to extract the effect of the displacement current in
I
electromagnetic.
think there is a problem of community here. We should agree on what we mean exactly. If I can try to interpret what Oscar is saying, that you would have an algorithm that is actually behaving to very high accuracy like Maxwell equations. Okay, that's what doesn't really, you probably, you know, I guess so.
Exactly, no, you're right. You will not write the, okay.
Okay.
Fosca, are you referring to the work of Tegmark and the, learning of...
I was simply saying that, so if you take, if you have enough data, you can really learn even very complex and things. Even if you have enough data for the election of the Pope, you can even predict the Pope. But the matter is that how many data you have, which how many. So in some sense, I'm confident. But you know what will useful if you have the Maxwell equation, an algorithm that behave like Maxwell equation, and you don't know, and you don't have the meaning.
You can infer relativity, which is not that bad. I mean, that's not that bad.
I think, Roberto, one thing that probably can, I mean, I work there, and I mentioned it, Tegmark published a paper called AI Feynman, which is this huge effort to try to build in a statistical way equations. So there is a way to embed an equation, and there is a language, and they try to learn equations. Now there is a subtle trick in the paper, which the machine actually spits out a lot of candidate equations to solve that numerical problem. And there is a student in front of that machine that tells AI Feynman, this looks like right. Wow, this is the Maxwell equation. That's amazing. Oh my God, I got the Maxwell equation. Now, they don't really explain how many candidate equations the student had to go through before fishing out that there was also the Maxwell equation in the prediction pool. So it's a bit of a...
When I see it, I trust. When I see it, I trust.
Yeah. No, it's just I'm on your side. It's just it produces a bunch of equations among all.
Like St. Thomas. You show me, I trust.
You see,
it was a Lagrangian, I think.
Already, if it spits out 100 equations, and one out of these equations or sets of equations, and one out of them is the Maxwell equations, that's quite impressive.
I do agree. Yeah. But how can you choose that out of the 100?
Now are much more.
How can you choose it out of the 100? How can you choose it out of the 100? Come on.
You need a human scorer.
One.
You need an expert.
Maybe the others are equally well. We didn't find it because we were satisfied with Maxwell equations. But
I think you can download the code and run it in a laptop. It like takes half an hour. So it's a cool experiment.
But it's let's say already to make it a bit more serious, already the restriction of the space of possible hypotheses to something which a human can check one by one is something which is which can be of enormous help and an enormous achievement.
If I should say something now, coming back to Ricardo's question about computational neuroscience, I know a part of that field, but a little bit about a part of that field, really, I should say. It's an enormous field. So it would be good if you, I can say something, but then maybe you can build on it and give more detail. What kind of connections do you want? Let's say in Sweden, computational neuroscience is dominated, or has been at least dominated, by people who do detailed models of individual neurons, and then detailed models. That means that they have some sets of ordinary differential equations, probably at least a few for the calcium dynamics and whatever, and then maybe different compartments of the neuron, and then some connection between them. And maybe in the worst case, they have many hundreds or many thousands of equations per neuron. And then the question is, which of these parameters of these equations are known or not is an open question. And then they couple these neurons, in silico neurons, to one another as they believe that they are coupled in the animal that they want to study. And if they're not sure, they do some random coupling, which is more or less like it is. And then they evaluate it by doing experiments on their in silico model, more or less as they would do in the lab. They have the lab animal and they excite some neuron and they give some drug and they see if they excite better or worse. And then they do the same thing for their big in silico computer software. Now, I think that's quite far from the methodology, at least of physics, but also of the algorithmic part of AI. And it's not easy to bridge that gap, and I'm not sure they are interested in bridging it on the other side. Perhaps they are actually not. So, Ricardo, can you please make this a little bit more concrete? Which kind of bridge do you want to see, and where do you think anybody would like to agree to give up their real estate on the other side, to have some bridge?
For instance, it's again about what learning is. And for instance, nobody knows what really the feedback signals are in neural circuits. This is one very important problem. Use an error signal in back propagation, say, for just for training neural network, but this is not clear how it's going to happen in the brain. Okay, this is one problem. Another problem is the neural code, which is again under many aspects not understood. Or another problem is the overparameterization. You know that you have 10 to the 15 weights, and you know that a large fraction of them is actually silent, and still we don't understand much about the computational role of this. So it seems to me that there could be common questions between the fields that have not been addressed. What you were describing was kind of some direct problem, like you want to build a model of a neuron. Okay, that's fine. That's a direct problem. We know how to do it, more or less. But at a slightly higher level, how can learning take place in a biological system which is highly overparameterized, highly disordered, and in which we do not really know what the feedback signals are, in which the coding is sparse, and so on and so forth. These are kind of almost computational questions that have should have a consequence also on the modeling side. So this, to me, this looks very fascinating.
Sure, I agree that it's very fascinating, but who is your counterparty? Eventually, neuroscience is an experimental science. So one would like to have some important experimental effort to connect such modeling, or let's say higher level, as you correctly said, higher level modeling effort should be connected to experiment in a meaningful way to make an impact. That's what I would like to say then.
Yeah, I mean, there are techniques now that allow to measure the activity, even though not directly, of up to say 10,000 neurons. So I mean, there's some progress. There is some progress, but I'm not the expert about experiments. I always rely on Nicolas Brunet.
I think you're frozen, or as me.
He's gone.
We lost it.
Ricardo is frozen. Ricardo Zecchina is frozen.
Yeah.
Okay. Now we can close. We can do everything.
Now we are free.
We are free. Freedom.
Yeah. Maybe Matteo, you can. If Ricardo is gone somehow, maybe Matteo, you can take over.
Well, yes. No, I already tried to be provocative with my question, and but I thank you for all your replies, and I think we are more or less. So Ricardo is back, and we are more or less at the end of this
microphone, Ricardo,
discussion.
Yeah, so there was a question by Francesco Ginelli. How much can you extrapolate? I don't know at which point he was asking this question. I don't know if Francesco, you want to...
Yeah, no, it was just, I was wondering about the claims of how much can you reproduce theory from data.
I see.
My point is that, of course, when you write a theory, either a very humble theory or the pinnacle of Maxwell, you of course write a theory which is able to reproduce hopefully all the data you have, but then can suggest a new experiment and new phenomena. So I always wonder, I always wonder how much is extrapolation possible with AI or with machine learning, let's say.
I think we all agree with you in the sense that it's very well known that machine learning works in a certain domain of the data, and if you move far away from that domain, it's probably not going to work. So the Maxwell equation would probably work in the domains of in the data domain, so in the regime which is described by the data that has been used to train. But if you look for a completely different regime, the algorithmic Maxwell equation derived by AI would not work. So I totally agree with you that that's the point. So if I can summarize what you said, I think that just to close, unless anybody has comments, I would like to say that, well, I think that some of you raised the issue of avoiding any hype, and I totally agree. Roberto Livi was actually saying this. So we should be very careful and cautious in making claims and just work in understanding. I think that about the issue of sharing data or sharing codes and so on, I mean, we didn't touch this problem, but I think that the natural consequence of this is that scientists have to organize in consortia. There's no way science can compete with industry. With, a small lab can compete with industries, and I think this is a potentially, I wouldn't say a danger, but it could be a problem for science, for the evolution of research. So so this is something to think about. And in Europe, hopefully something is going to happen in the next years, because otherwise Europe is going to remain quite behind. I think we all pointed out at the end that causality, either in terms of interpretability or extrapolation and so on, is a big issue, and also the issue of improving supervised learning is also a big problem in the sense of all the data of this type, as you were mentioning, and in this sense, the role of embedding is also really crucial to improve algorithms and to hopefully go beyond what is just creating correlations, what we are actually doing right now. So there's a lot of work to do, and clearly, from the point of view of our community of statistical physics, actually we have a kind of nice object to study. So there's a lot of work from a theoretical point of view, but it's also true that they can be very useful in applications. And so, yeah, I mean, it's very difficult to make predictions in the near future. So we should have another discussion like this in a couple of years and see what has happened in between. So anybody wants to say something? Or I just thank all the speakers. Thank you for being here. Riccardo, you're in the US, right? So
indeed.
Okay,
Boston.
so well, it's a reasonable time. Okay, so it's not 6 a.m. So it's fine. Okay, so thank you very much and thank you, Eric, for coming back from holidays. And thank you, Martin, for your participation. Thank you very much, Fosca, to be the outsider. The outsider from computer science here, but I think it's very important for us to...
I managed to be provocative.
Yeah, I think that Roberto Livi is now wondering. So I would like to thank all of you, and thank you for the questions and for the participation. Okay, so
thanks for
inviting everybody.
Bye.
Thank you. Bye.
See you another year.
Okay. Ciao a tutti.
Ciao.
Ciao.
Bye.
Ciao a tutti.
Ciao.
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 Rafael, thanks to all for organizing.
So siamo rimasti pochissimi, se stanno andando via tutti, quindi il congresso is over, siamo in 9, quindi vabbè, vi saluto.